Over to you, Riva.
Yes. So, a very good evening to all the distinguished guests and faculty present virtually with us today. I warmly welcome you to the inaugural day of the AICTE Training and Learning Academy sponsored 1 week online faculty development program on Shaping the Future of Manufacturing with 3D Printing Techniques, organized by the Department of Mechanical Engineering SPCE. Sardar Patel College of Engineering was established in 1962 in Andheri, Mumbai. It is one of the oldest government aided engineering colleges in Maharashtra and has played a pioneering role in advancing technical education in India. The institute has produced brilliant graduates who today serve as leaders, innovators, and change makers across industries in India and abroad, who not only excel in their technical fields but also carry a strong sense of responsibility and ethics. This event would feel incomplete without remembering Dr. K.M. Munshi, the founder of Bharatiya Vidya Bhavan. He was a visionary freedom fighter, lawyer, and statesman. He believed in blending modern education with deep cultural values, and his ideals laid the foundation for institutions like SPC to inspire generations of students to pursue excellence with integrity. Today's program is a reflection of that vision. Just as Dr. Munshi believed in constantly advancing knowledge, we strive to stay updated with the latest developments in engineering. With the rapid evolution of manufacturing technologies, especially additive manufacturing, design and development of products is being redefined. To keep pace with these developments, this program has been organized to make our faculty members well versed in these innovations, as they are shaping the next generation of engineers. And this program helps improve the quality of engineers that SVCE produces. So, without further ado, let us begin with this event, the way we always do, by invoking the blessings of Goddess Saraswati, the embodiment of knowledge, wisdom, and creativity. I request everyone to kindly join in for the Saraswati Vandana and the digital lighting of the lamp, symbolizing enlightenment and new beginnings. Now let us proceed. I request Dr. Bhasme, co-coordinator of the Faculty Development Program, to address us now.
Thank you, Riva. Good evening to all the respected dignitaries. Dr. M. Muridi sir, in charge principal, Sardar Patel College of Engineering, head of the Mechanical Engineering Department, Dr. Santosh Rane sir, distinguished speaker of today's inaugural address, Dr. Guru Prasad Rao, Director, Mudgolaya Design Solutions LPP Thane, other distinguished speakers, other faculty members from Sardar Patel College of Engineering, deans from Sardar Patel College of Engineering, coordinator of this ATAL FDP program, Dr. Kiran Bhore sir, fellow academicians, and enthusiastic participants. On behalf of Mechanical Engineering Department of Sardar Patel College of Engineering, Mumbai, it is my privilege to warmly welcome you all to this 6-day ATAL Online FDP Development Program on shaping the future of manufacturing with 3D printing techniques, scheduled from today up to 6th December 2025. This program brings together an exciting blend of 13 expert-led sessions designed to provide deep insight into the evolving world of additive manufacturing. As we stand at the forefront of the rapid technological transformations, 3D printing has emerged as one of the most revolutionary innovations, reshaping design thinking, manufacturing processes, and industrial applications across sectors. Through this FDP, our aim is to equip faculty members and researchers with the knowledge, skills, and future-oriented perspective needed to integrate these advancements into academics, research, and industry collaborations. So we immensely grateful to the AICTE ATAL for giving us opportunity to host this FDP and for continuously encouraging the capacity building among educators. I also extend my sincere thanks to our eminent speakers for accepting our invitation and for shaping their and sharing their expertise with us over coming days. To all the participants, your presence reflects a strong commitment to continuous learning, and I am confident that these 6 days will offer valuable learning, active interaction, and meaningful networking to you. Once again, I extend a warm welcome to each one of you, wishing you a productive, engaging, inspiring learning journey throughout this program. Thank you and welcome. Over to you, Riva.
Thank you for your insights and kind words, sir. Now, I request Dr. Santosh Rane, Head of the Mechanical Engineering Department of SPC, to kindly say a few words.
Riva, actually, Rane sir is traveling in the train and is
Yes.
outdoor, so could not connect. I mean, he was there on board, so we'll connect
Yes.
him later on. Okay, we proceed.
Okay, sir. Okay, sir. Now, I humbly request our principal, Dr. M. Mordi, to address us.
Thank you. Distinguished speaker of this today's inaugural function, Dr. Guru Prasad, the coordinator of this ATAL FTP, Dr. Kiran Bole, and co-coordinator Dr. Basme, and my faculty colleagues, and all the distinguished speakers and dear participants. I am glad that the Mechanical Engineering Department has organized this 1 week ATAL online FDP on shaping of future of manufacturing with 3D printing techniques. So I'm very glad for this event, and this online FDP is going to be for the 1 week, and there are a number of sessions that Dr. Basme just informed you. So I'd like to brief about our institution for the people who are from the other organization. Sardar Patel College of Engineering has been started since 1962 by Kulpati Munsiji. In the beginning, that the institute started with only 3 UG programs in core branches: civil, electrical, mechanical. Now, over the period of 63 years, the SPC has a glory of 63 years, and over a period of 63 years, the institute has grown significantly. Currently, the institute offers the core branch in 3 disciplines, that is civil, electrical, and mechanical. The institute also offers 4 PG programs, that is 2 in civil engineering, that is structural engineering and construction management. And in mechanical, the institute offers PG program in machine design, and in electrical, the institute offers PG program in uh, PEPS, power electronics and power systems. Apart from this, the institute also offers PhD programs in all the 3 disciplines. The last the year before last year, so we have started the new program, that is new UG program for working professionals, civil and mechanical, with 30 intake. And also we have increased the intake of MTech structures and construction management from 18 to 24, looking at the good response from the candidates. So all seats are full. So now, yes, Saturday there was board meeting. So the board has approved to increase the MTech structural intake from 24 to 36, and also CM construction management from 24 to 30. We are also going to start working professional program for MTech program in structural engineering for working professionals, and also UG program in um, electrical engineering for working professionals. And coming to the quality of teaching learning, I'm glad to inform you that all the 3 UG programs have been accredited by NBA, civil, electrical, and mechanical, up to 2028. And also the institute got autonomy from since beginning, since 2010-11, and the validity of our this thing autonomy is till 2027. So being autonomous institute, a lot of activity in changing the curriculum, and we have implemented NEP, that is National Education Policy. Already we have 2020 we have implemented, so that has changed the curriculum drastically. So now the focus is on not only teaching, so learning through practice. So we have a close interaction with industries. And one more important feature of this NEP is that the last semester, one semester, all the students have to undergo the compulsory 1 semester internship. So that will add the value to the our degree program, and definitely the the job prospect will definitely improve. Our students will get better jobs with this internship facilities. And also one more important thing is that silent picture of this NEP 2020 is that all the students will get major degree in the civil, electrical, mechanical with minor also. They will get minor degree also. So there are some, each department has means offering certain minor programs, including mechanical engineering also. So that will also add the value to our degree. So this is all about brief about the institute. I am sure that this FDP will be very much successful, and it will be very much beneficial to the all the participants. So I am looking on the screen now. The more than 150 participants have joined. I think that registration must have been crossed 200. I suppose. I don't remember. I don't know exactly. So it is a huge response for this program. This program. I wish this FTP a grand success. And I thank Dr. Kiran Bole and Dr. Basme for organizing this ATAL FDP. Thank you.
Thank you so much, sir, for your inspiring words. Now, keeping in mind the objectives of this program and the thoughts shared by our faculty members, let us begin with the Faculty Development Program. Our first session is to be conducted by Dr. Guru Prasad Rao, who is the director and mentor of More Kalya Design Solutions LLP, a leading 3D printing and advanced manufacturing company in India. Dr. Rao has 38 years of experience in this field across academia and industry. He has taught at IISc, NIFT, SPJIMR, and more, and mentors tech startups through KIIT TBI as well. We are honored to have you with us today, sir.
Over to you, Rao sir. Hello.
Yes, yes. I was in a different screen trying to organize my slides. Um, I think it is a wonderful program. I see a lot of familiar faces here. Um, Thanks for this opportunity, Professor Kiran Bole. Thanks for organizing it very well, Professor B.N. Pasme. Thanks for your kind introduction to the program and institute, respectful principal, sir, and Reva for a very kind introduction. And I think today we are going to discuss many aspects which augmented by other speakers over 1 week. It is a very interesting thing. I only feel, I should also get this such opportunity. Many times as a speaker, I get to speak, but I think there is a lot to learn also. And today, we will be very soon, 6:30, we'll start the presentation. I wish all of you happy learning. And also, it is a quite intensive, uh, starting from morning till evening, or it is starting only in the evening, sir? I can clarify, because I have not seen the program.
It's only in the evening, sir. It is online. ATAL is online ATAL especially. Online
Okay,
ATAL is
okay,
framed for the
okay,
evening. From it starts from the 6 to 9 o'clock or 9:30 on the first day, because
great,
of the inaugural, which is for the 30 minutes.
great.
And
So
only on Saturday, which is the last day, it starts at 2 p.m.
I see. Okay, so I think it's a wonderful opportunity for all of you. And after a day's hard work and exam duty, corrections, classes, I think faculties have to sit in front of a computer, or maybe some of you on mobile if you are moving, seeing this. We'll try to make interaction quick and easy. And toward the end of my session, I'm also having a Q&A. So some of you who have some pressing questions, I'll try to answer, because asking question is easy. Answering questions are not always possible. It's a tough job, always. Even whatever a number of years you have. So back to you, sir. I'm very happy to be here, and I push it back to Professor Kiran Bole.
Yeah, thank you, sir. Almost we finished the inauguration well in time, and it's 6:26. I see in my clock. So if you can set your screen and all those, so we can start at 6:30. Almost the participants on board are ready to receive the things. I know. I mean, you as a practitioner, I mean, worked so lot much in the 3D printing area, so it will be a wonderful treat to all of us.
It will be my pleasure, sir. It'll be my pleasure. I'm trying to share the screen. Share the screen. Allow share screen. Share this window. See if you are able to see my continue to share. Can you see the presentation, sir?
Yes, sir.
Uh, Not presentation, we are not able to. It was there, but I think you come out of it.
Oh, I
Can you
see.
see once again?
Let me check.
Mhm.
Is it there now? No.
No, sir.
No,
I
not
think
it.
you have to share full means full
Entire screen.
screen instead.
Entire
Entire
screen.
screen.
Allow share window. Allow
And
share
entire screen
screen.
will be better to go.
Okay. Now, can you see? Are you able to see my screen?
Not yet, sir. You choose the entire screen option,
Share
right?
entire screen.
Entire screen. Yeah. Now it's coming. Yeah. Perfect, sir.
It has come.
Yeah, yeah. Perfect, perfect.
Wonderful. We are having exactly. We are on dot 6:30. Uh, very good evening to all my faculty, friends, colleagues, and those who are enthusiastic to join this FDP program today. We should thank Sardar Patel College for arranging this under the aegis of ATAL, AICTE, a sponsored program on shaping the future of manufacturing with 3D printing techniques, 1st to 6th December. And today, since this is the inaugural talk, I'll be focusing on 3D printing and future avenues. There are a lot of things, gaps which we need to fill in because many speakers over 1 week will be giving same things with a different depth, greater depth, I should say. And so today I'll confine myself to talk more about the broader aspects which are concerning 3D printing and future avenues. Future, as you all know, is VUCA world, volatile, uncertain, and anything can happen with regime like US regime now. A lot of things are going to get a hit, but hope is the only thing which is going to change. So also technologies, new technologies are bound to come with the same hope, which will come and increase the capabilities, efficiencies, reduce cost, give you more value and whatnot. So let us go on this journey. So my talk will essentially touch upon introduction, historical evolution, principles and process of additive manufacturing, benefits of additive manufacturing, current application across the industries, challenges hindering widespread adoption, future avenues of 3D printing, which is the focus, ethical, social, regulatory considerations. Then we have a road ahead and conclusion. So we all know 3D printing is a new way of making things. Okay, we had subtractive manufacturing. In fact, many times I keep telling people there are three types of different ways things can be made: the plus process, the minus processes, and zero processes. I don't know, many of you may be familiar with this. The plus processes are many things, like painting is a plus process, welding is a plus process, gluing is a plus process, plating is a plus process. A negative, anything which can be removed. It could be, turning, boring, drilling, all these, or subtractive or conventional processes. There are processes which are called formative or zero processes, which are kind of, you don't have any addition or subtraction, like rolling, for example, wire drawing, for example, coining, for example. all these will form the zero processes. So today, the conventional processes have been there for last 200 years and more. The new way is additive manufacturing, right? In conventional, you needed jigs and fixtures to have the perpendicularity, parallelity, concentricity, and all that. Uh, but additive manufacturing is not like that, where in one setting you can do many things, as you can see on the right hand side. So it is a fabrication of material layer by layer, but layer by layer is not a sufficient condition to declare something as additive manufacturing. You know, you will have to ask me question why. Later we'll take it. But digital model is the sufficient and necessary condition to call some process as a additive manufacturing. Now tell me, CNC is also having digital input data, STL or step files. So can it be called as additive manufacturing? No, because CNC is subtractive, right? It is subtractive. So many times this 3D printing is also called as additive manufacturing with a great promise that it is going to enter manufacturing. For me, manufacturing means making millions, not one or two, right? But additive manufacturing is something which people have kind of, they want to see that coming. And somewhere we are coming close to it, AM, right? That is very important. And this is myself way back in 2000, 2003, working on this Prodigy, a FDM mission by Stratasys with support separate, model separate, material. I was running it in IISc Bengaluru. It was in 93. I just saw one 3D printed object. In 90s, we studied this technology. So it's a long way. I've been practicing this, technology. So looking at this transformation, art to part, is very, very important here. You know, how these objects are created in digital media, 3D model or content creation, 3D content creation, then that is given to a robot like device called 3D printing, 3D printer, and it is going to recreate it. With the transformation, we can change many things. So it's a regime where we create a part directly from CAD, CAD to part transformation. So this is like a paradigm shift, which has never happened before, you know, and this is going to de-skill. People wanted to have some skills to make prototypes rapidly, but those are not required. You don't have to be a model maker. Now you can actually create things. So this gives you a better design freedom, reduced material waste because you don't have to remove material. You're adding material, what is required. Accelerated innovation cycles because you can fail early, fail fast, and move on so that you don't have to waste time lingering on something which worked or did not work. You make a thing, you test it quickly, it fails, then you have another way. Go back to drawing board and again reiterate. Over the past 4 decades, the scope of AM has expanded from what it was started with rapid prototyping to tooling, production, mass customization, and increasingly distributed manufacturing ecosystems. What exactly is distributed manufacturing systems? We can have a concept of cells across the country, across the globe, where whoever gets the order nearest cell will deliver it, make it and deliver it. That is called as distributed manufacturing ecosystem. In order to reduce the so-called lead times, just in time can be lived, by this kind of technology grid, which is distributed manufacturing system. And it is an ecosystem. And when we say 3D printing is, it is not just everything, there are many things which are there. I'm sorry about this slide. There are some changes which has happened. What enters the value chain here is idea design on left hand side. At the right hand side, you have the applications for which this technology is used. Now, in between, you have in the middle, you have 3D printing. 3D printing cannot be done without an idea, without a 3D CAD, without a pre-processing, you know, and also it cannot work without materials, without a proper care and handling of 3D printer. And even to create CAD, you require a lot of things like how to design for AM. Design for AM is very important. And in order to get CAD, sometimes we go by feature-based design or geometric modeling or by reverse engineering also, RE. So these are the inputs which they go into CAD. After CAD is made, we export the part. We have seen the earlier animation also. And always there is a pre-process. You make the whole object, you know, into several layers, and you're giving each layer to this printer. Printer prints one layer, and only beauty is a 2D printer is converted to a 3D printer by having a Z movement. That is, the table on which the 2D is getting drawn is incremented by a thickness, right? And that's how you get 3D printing. And materials, you can feed materials in the form of filament, liquid, whatnot, metal, non-metal, composite, glass, biomaterials, different colors, different properties, smart material. So many things are going to be there. A big palette now. When I started in 2000, we had model material as ABS, acrylonitrile, butadiene styrene, ABS, the composite, plastic, engineering plastic. And support material was having same material with lot of chalk in it. So it used to appear gray in color. It used to break very easily, brittle. So it meant for easy breakage because it is support. After all, you have to breakaway support, right? And post processing, everything what is getting printed on, it is like a masala dosa is made. You need a spatula to remove the dosa, otherwise you cannot take it out. Same thing, 3D printing, whether it is in polymer or metal, you need to take it out of the build platform. So we call it as post processing. Not only just that, we have to remove the support, we need to clean it, we can sand it, or probably we can even do special treatment, buffing, polishing, plating, painting, laser marking, many things. When it comes to metal, there are many others like wire cut EDM, short pinning, acid, cleaning, etc., will come depending on the material. After this only, each component which is made will join the world of applications. As global supply chains face tightened vulnerabilities, just like you had in COVID time, people are looking now. How can we have a digital factory wherein we can have AM forms or 3D printing forms, wherever whoever is nearest will get that, and they make it on demand. And exactly this was done during COVID time. And COVID, a lot of emergencies were there. I remember at Imaginarium, we were doing many things like ventilator splitters. They were not available because global supply chain was affected that time. Ships were not moving. So we had to make it available, on demand. And digitally, those things were transferred. It was shared without any IP those days. And I think it is a very good demonstration. Now, coming to the cloud factory, you can see people, not everyone can actually own printers. MSME OEMs, they have small and medium printers, large size printers or OEMs will have, okay, bigger ones like Boeing or Maruti or Tata Motors, they'll have large systems. And many times individual designer maker also want to do something. So all these are increasingly coming to what is known as online, factories. Okay, and today it's a new business model. If you have a CAD, you have a opportunity to showcase it. You can get it built by somebody else and delivered to the customer. Okay, so it is transforming so-called the supply chain to a demand chain. You know, the customer will look at and then he will pull the products, right? Supply chain has become demand chain. That is the transformation, what we can see. So today, 3D printing impacts a wide spectrum of sectors: medical, automotive, aerospace, construction, consumer goods, energy, and defense. We can see there is a huge capabilities, changing capability that we have seen. What we used to do in the early days were mostly prototypes, term models, mock-up models, what we used to call, to a design validation model in the middle, 2010 onwards, and then we have end user part in 2016 onwards. Almost we have 1 decade we have come, from that 2016. Almost we are in December 2026 is close by, so it's a decade, right? And so you can see the capability today. On demand, one off part can be made and delivered to the customer. There is no economic order quantity here. Economic order quantity is one. That is the beauty of the whole thing, and people are happy. you know and what's more, people can actually design themselves and give it to these 3D printing companies to ship them the part what they have. So it is like democratizing design that is happening. So today there are many new frontiers that 3D printing is addressing, such as multi-material printing, bioprinting, hybrid manufacturing, 4D printing, machine learning driven process optimization, promise to redefine the future of manufacturing is happening today. So I think the whole thing will revolve around demand chain here. Every user wants to wear something unique. They will design themselves and demand that to be made for them, and in a record time. So there is a lot of pressure on quickly make it and provide. And that's where the technology is also there, ready to deliver it. Historical evolution of 3D printing. We know historically 3D printing has been attempted by many people. I can say even nature prints everything which is additively made, right? We ourselves are additively made. In 9 months, we are delivered with a bionic eye, a CPU, a brain, and the pump, a natural pump, heart, etc., which are hard and soft and transparent, opaque, whatever, multi-material, exactly, and it's living, right? It's something even more than 3D printing. So if you want to look at 3D printing, you have to see nature, uh, always. And historically, people have been trying to make prototypes quickly, and that's where they looked at photo polymerization as one of the methods. Dr. Kodama actually, in 80, he brought in the name also, rapid prototype. Unfortunately, his discovery could not be patented because he had no funds. And it was in 84 or 86, 84 it was applied, and 86 it was awarded to Charles Hull, Chuck Hull. And That's where the stereolithography or 3D printing, SLA. Many people will be wondering what is SLA is. It is stereolithography apparatus. A stands for apparatus because the whole thing was looking like a small apparatus in a lab, right? And I'm not showing all the photographs today because I've been talking on the same subject for a long time. I didn't want to use the same old files again and again. So I think you should look up or you do some exercise to find that how the first stereolithography apparatus were looking like by Charles Hull. And there they were able to uh, quickly solidify a photosensitive liquid, with ultraviolet, and the whole thing, redefined the way things are made. Because it was patented, people had to circumvent, and this is what led to other things. Like in 1990s, we had FDM coming, SLS coming, electron beam melting coming, many more, even LOM coming, you know, because they wanted to circumvent those technologies. They want to create 3D printed, a new methodology for 3D printing or rapid prototyping. Still, it was called as rapid prototyping till it was in MIT. They came out with binder jetting, or it is with adhesive. They were able to consolidate powder, and they called it as 3D printing. You know, and it was MIT had this trademark 3D printing. But since people were freely using it to describe other things, like FDM also is 3D printing, SLA is also 3D printing, SLS is also 3D printing, E-beam is also 3D printing. So they gave up their right on 3D printing, and 3D printing became a generic name. So please understand 3D printing is a set of technologies, not one technology, that makes the object layer upon layer, right? That this gives the definition from a digital input data. Okay, that is also very important input. And digital input data can be from a computer program, or it can be from a scanning. Any doubt? Anyone? I'm here some. I hear some sound, sir. Revas, there is some sound in the background. Okay. In the early 2000, many open source initiatives such as RepRap came. There was a this led to the um, uh, so-called the makers printers, open source makers printers all over, cheap replicas of FDM technology came. RipRap is the printer is able to replicate itself. Replicator, 3D printer printing itself. Most of the parts are done. Literally, I've seen this with HP's what is multi-jet fusion. Multi-jet fusion, which is an advanced printer, has 50% of the parts of the printer printed by the same technology, multi-jet fusion, MJF. HP's 3D printer, a wonderful technology. And that's how the promise, what was made, it got realized much later, but the capability was realized early on. So this democratized access to affordable 3D printers, and this led to lot of new innovations. In fact, FDM had several other avatars like SCARA. Then you had um, uh, Delta printers, and those are very much like FDM, but the way they are driven, where the head is used, where the table moves, is going to make a difference. Yes. Over the last decade, improvements in mission speed, reliability, resolution, material science have enabled AM to go beyond prototyping into end use part fabrication and manufacturing. So this is the beauty of it. Today, Siemens makes all their earplug for custom hearing aids and all by 3D printing only. They take the scan of the user ear canal and they make it custom built. And how many of them? Some thousands of them they are making. They are not having any other process but 3D printing to make this. So it has become kind of AM already. Today, AM is recognized as an important player in Industry 4.0. Industry 4.0 is interesting, for me, it is coming full round. We started with so-called um, the CAD, CAM. Before that, there was conventional manufacturing. And during conventional manufacturing only, we started automating them with MRP 1 and MRP 2, right? MRP 1 was material requisition planning. MRP 2 was manufacturing requirement planning. And this led to further ERP. But ERP always suffered from design data. So they had something called as PDM, product data management. When they combined these two, product data management and the ERP, it became PLM, product lifecycle management. And when product lifecycle management across new technologies, when they are taken, what you are going to have a new age called Industry 4.0, which has got so many components enabled by uh, the information technology and communication technology. These are the two drivers of Industry 4.0. Sensor technology, it is able to, we are actually having a regime which is a kind of it is not like a fixed date. It is going to be a band. It is still going on. We are today, it is current. Industry 4.0 is something current. We are in the beginning of that. Maybe in some areas we are already in advanced stages. In some areas we are still entering that. And in that you have something called physical cyber systems. And in physical cyber systems, the physical side is brought about by additive manufacturing or 3D printer. I always say 3D printers, the robots and CNC together they form a deadly cocktail of manufacturing trinity. We call the manufacturing trinity. In future, everything what you want will be manufactured by three things: additive manufacturing or 3D printing, a robot will be there to handle, and a CNC machine, all controlled by all this component what you see on the board. Principles and process of 3D printing. I think this is something which you will be deliberating in coming days. What I'm going to give is only a very, very small intro of this. AM encompasses several technologies, each defined by its energy source, material type, method of deposition, and solidification, right? And so you can see they come in all shapes and sizes, different colors. I love all of them as a user because each one is a beautiful technology. We cannot say something is bad, something is good. They're all good at a particular thing that is important. They may be bad at some other, but we are looking at what is the goodness of each one of them. I've added here bioprinting also, which is not part of this, but there are a lot of systems which are coming, which are again part of these only. How to deposit. Each AM process offers unique advantage and challenges. Their convergence is giving rise to hybrid technologies that blend additive and subtractive methods for improved accuracy, surface finish, and material integrity. Talking of surface finish, I remember always the 3D printer, which is called SolidScape. SolidScape is essentially used in jewelry or medallion making or figurine making. What they do after deposition of the wax, the surface area is very bad. You know, there is a waviness on the surface. So at the edge, there is a milling cutter that comes and mills that, thereby giving a very nice surface for the next build. Every time it does. See, the hybrid technologies, they beautifully blend additive and subtractive methods. Is a good example in Soldscape, which is quite expensive because it combines these two technologies. A controller is quite complicated. The G and M codes have to be separated. It is two channel, and so the expense. But quality is superb. Benefits of 3D printing and additive manufacturing. There are many benefits, of which one is design freedom. EM allows us to design structures that are not possible previously by conventional manufacturing wisdom. Like there were hard grammar, what to do, what not to do with the earlier fabrication technologies. We had DFAM, design for assembly, design for manufacturing, design for that, design for this. But design for AM is a new approach, new thinking, a new culture. The complex geometries were hitherto only made by man. Even today, our hand dexterity is so good, we can carve out anything. People have made हाथी का पत्थर का हाथी का अंदर हाथी एक उसका पेट में एक हाथी ऐसे भी बनाते correct, no? Nothing to beat human dexterity. But coming to digital manufacturing like CNC, it is not possible because there is a lot of undercut that is there which they cannot manage. So internal channels, lattice structures, topology optimized shapes, these are all possible only because of additive manufacturing today. Because you have a control over each layer. Not only just shape you can control even the property. That means I can have two different material mixing. You know, each layer a different material. I can have bi-material. When I say bi-material, then that is going to introduce, give us a new opportunity to try the 4D printing. Okay, we'll come to that later, but I'm sure one of these sessions, a week long, you have, will touch upon those things in much greater details. You can see some of these are very complex. It is unimaginable, and it cannot be produced at all by normal manufacturing wisdom, right? Why unimaginable? Well, it is like you have a mathematical equation driving these curves. You start giving n is equal to 1, 2, 3, 4, and start getting new proliferations, just like a kaleidoscope, right? At every change in n, you get a new shape, and you freeze wherever you like, and you just save it as a solid, give it to 3D printer, it prints. No questions asked. Some of these are impossible to even imagine, unimaginable shapes. Customization and personalization are very important aspects. Be it a custom jewelry design, custom implant, custom device, a custom footwear, all these are something which will go by the anthropometric dimensions of the user. Anthropometric dimension, that means each one of us are different size and shape, right? We are unique people. So in order to have something designed, made for you, it is not just customization, it is personalization, right? And individualization, in fact. These are new terms which are coming, you know, because of the beauty of this additive manufacturing, you can do one-off. So these things are possible, and it is not going to be demanding anything extra wage, extra compensation. You can see here, this is a wedding ring. I made it. You can see what is you see in blue color, light blue color, is a wax model. The bride and bridegroom's, finger thumbprints are taken, to personalize this with names inside, which is going inside the shank, and there it has been additively made in wax, then cast in metal using a, lost wax process or investment casting. And this is actually gifted by me. It exists. You know, it is not a concept. Material efficiency. In fact, many times we say near net shape. What is near net shape? So you take a cylinder, turn it, and make an artifact. Supposing that artifact you can make it directly, it is gross size, or what we call net shape. Net means gross, right? And that is possible by additive manufacturing or 3D printing, because we have layer upon layer build. Only what is needed is deposited in the same shape as you require in the end, and the in between, the two layers we are going to fill to get the solid section. It could be of many nature. You can have some honeycomb also there, and these are all impossible by conventional manufacturing system. And scrap is minimal, you know. So you can see here the conventional manufacturing wisdom, so much of chip is generated, right, by turning or milling, but the artifacts on the right hand side are all made by additively. They're made as net shape, gross shape, what you see. There is no chip here. That is the beauty of 3D printing or additive manufacturing. On demand production. What is on demand production? AM supports decentralized manufacturing, enabling parts to be produced as needed. There's no need to carry inventory, and you can have a digital inventory. And because of which, you can have a very short supply chain. Locally, one can have a industry supplying things. It need not have to have a highway or a transportation, an elaborate system of network of those things to actually carry out this. And we had earlier also mentioned about the decentralization of manufacturing, and I think that's really what is going to ensure just in time, and just in time production, just in time supply, just in time consumption. In the load centers, suppose you want to have a drug to be made, you can have a 3D printed drug ATM actually put in the tertiary care center, or where people want to buy. You don't have to have a factory and make it, but you can actually have it in the make it in the tertiary care hospital only. Drugs can be given like a ATM. It can be done. People are working on it. And rapid prototyping and innovation is something which continues, because of its ability to make a form fit and function can be checked quickly. One can make a model, small model, a dumb model, or a low fidelity model, or a high fidelity model, depending on what is the nature of evaluation. These are all simulations. What is rapid prototype is, after all, a simulation of a final product. So how can you test it, quickly make it and test it with the target audience? You can give it to people quickly. It doesn't need a tooling to be done or manufacturing to be done. And so you can find the feedback quickly coming to you. So if there are any feedback which are good, it's okay. It is going to reinforce you're on the right track. Suppose it fails, the testing fails, then also you're happy that okay, after all, that is not the way. So it becomes very important in innovation. Innovation is not invention. Many times I keep telling, innovation is about the impact of a invention on impact means it could be societal well-being, that is somebody using it and they're comfortable, have a better uh, life, uh, or and also having a profitability, creation of wealth, you know and this is what is called as innovation. you know so idea could be having a potential to be innovative, but you will never know. So it is very wrong to say innovative idea, because you will never know what comes after that, whether that is the end or there is another iteration you're going to make it after the feedback is received. So see, these are called as development cycles, and the whole thing gets accelerated. That is very important. Lightweighting is something, a great advantage you have, particularly in technologies like SLS. One can have a nested product, a product which is pre-assembled, because the support here is powder, and in CAD you don't have any gravity, and so you can have a ball inside a ball inside a ball. You know, as long as you have some means to remove the powder in between, you know, after removal of powder, all these balls will collapse inside. So, in fact, these models used to make to show people. I don't have those models. I would have shown otherwise. These are wonderful things, and these are achieved by lattice. It is like a sponge-like structure, a structure which can be seen readily in nature, like bone structure, or what we have, the coir structure, or sponge. All these have lattice, and the lattice can be regular or it could be um, varying functionally. Sometimes we call as the functionally graded material. When we go to material, we'll discuss that. They have a kind of polarization of the strength that is required. For in a particular area, you need something to be strong, something to be lighter in on the other side, just like in bones. In bone structure, if you take a section of it, you will see all this. They're optimized geometries. The lattice structure is made such a way, wherever strength is required, where resistance is required, you find closer density, and wherever you need light weight, you have a sparser density. So the whole thing can be simulated in CAD, and what you can get in CAD, you can 3D print it readily. And today, the greatest beneficiaries of this advantage is aerospace and automotive. One may ask, aerospace, we can understand why automotive. You should remember, automotive was not really worried about, because it's a terrestrial mission, why they should have. It is not airborne. Airborne means you need lightweighting. Payload is very important there. But automotive industries are shifting from so-called fossil fuels to um, EV. EV, the petrol tank after filling and before filling, there is a lot of difference in weight. So the whole body of automotive, system depends, because it has got a kind of a payload which is there, which is going to give it some kind of advantage, because fuels get depleted. Whereas in EVs, the batteries, before charge and after charge, the weight will be same, right? So there is an increased need for making this lightweight to have a mileage. Okay. Of course, we have drones, we have airborne space systems, we have missiles, we have intra heavenly stellar bodies, vehicles, the skylabs, whatnot. All of them, they need lightweight, because it is an advantage, energy advantage without compromising on strength is having So that can only be achieved by 3D printing or additive manufacturing, what we call. So you can see, we can summarize this. There is something called as part consolidation. These are the 6 smart applications of AM or 3D printing. Part consolidation. What is part consolidation? It is combining all the so-called different parts that make up a product to fuse them together as one product. So bill of material will have just one part. That's it. So how it is done? So here, uh, conventional wisdom had welding, riveting, threaded fasteners, gluing, so many other things, and they were also not able to make it together, all built at once was not possible. So they were dividing it and then putting them together by a fastener. Today that is not required, because additive manufacturing is going to help make those impossible designs possible. So part consolidation, today they have achieved 20 parts to one part, 300 parts to one part in aerospace. And what is the advantage of this? Advantage lies in the reliability of these parts. Their cost will go down, manufacturing cost will go down, the reliability will go up. Their, they don't have to keep it as an inventory. They can just print it on demand. Many times, people look for on demand production, because it is a lot of material that is required to be held in a warehouse in order to even the spares. Today, that is not required. The second most important thing why people use 3D printing today are jigs and fixtures. So jigs and fixtures are very important with the electronics increasingly becoming uh, miniaturized. These production houses are needing a constant change in their jigs and fixtures. You know, you can always have a variable fixture, but like a clamp, but they're going for some jigs where you have to even have the guiding. You know, um, well, they're using 3D printing here. Need for lightweighting, we have just now discussed this. So you can see some of these having a lot of voids. You know, be it a furniture, be it a pillar, be it a aerospace structure, lightweighting without compromising on strength will be a great advantage. You know, and it will give you a longer mileage, lower fuel consumption, etc., etc. And coming to complexity, we Indians have a lot of these jewelry which are very complex, and what you see here is intertwining, loops with diamond setting and all. Very difficult to even imagine how to program it in a CNC. By hand you can do it. Hand you can do anything, but by machine it is difficult. So complexity, and also gold is something, more you touch, more you lose gold. So near net shape has really the greatest profound influence on jewelry making, particularly with gold, silver, even platinum becoming very, very costly nowadays. People will be forced to go for a near net shape creation of these, and that is possible only by 3D printing. And whenever you need just one part, you know, for example, if you are making a spacecraft, every spacecraft will have very unique requirements. So they are all custom made, and that is one part. It is not so manufacturing will lose its the word label. Manufacturing will go. It's fabrication. When you say one part, it is more like, your custom house, for example, custom uh, you know um, um, fast food, for example. You go to the so-called Subway to make your own um, sandwich. Why? Because you're the boss. You can order a sandwich, which will have how big should be, what are the toppings. You're going to decide. Same way, if somebody is commissioning it, you know, it is made for you. So you have to consume it, and so it's possible. Need for one part is increasing today, increasingly even in engineering parts. Need for customization is, as you see, whether it is artifact made for wedding ring or in the form of wedding ring or a custom implant for a cranial plate, what you see here, they have to be made in. Yes, yes, ma'am. You have any doubt? We can have interaction, no problem. Please repeat your
Sir,
question.
I think, yeah, I think we'll take questions after at the end or now also. Okay, sir.
I'm going to complete in a short while now, and as you're moving, you know, questions. If you have any very urgent question, I can take it now.
Yes, sir. Continue, please.
Anybody having a very pressing need to ask question now, I can take that. No problem. Otherwise, I'll continue. Current application across industries are many. I'll not go deep into every one of them because I know if I complete all the course and contents, what others will do. I will not touch upon these things, but I'll just list them. Aerospace and defense. Defense today is becoming very strategic thing. Defense for peace. It is not for war, it is for peace. Uh, Okay. And so deterrence. You have the capability and I have the capability. So be careful. So that kind of deterrence. Today, wars are very rarely done. With very powerful to very weak people, there is a war. But whenever they are equivalent, wars are not happening. That is very interesting. Automotive industry, as you know, each car is made up of uh, it used to be 30,000 parts earlier. It's all coming down thanks to part consolidation. So because of part consolidation, better reliability, the systems are changing from IC engine to EV. So a number of parts are changing. This you can imagine like how a mechanical watch today has become a quartz watch. A quartz watch has still gears, but very little, very less number, right? Mechanical watch, the complexity is so high, right? At Titan, I used to have a watchmaker lathe. We used to make very precision gears, you know, and shafts, which are only to be seen under microscope. Okay, all mechanical. Today, because there is a quartz technology, there is a taper motor, the whole gear system has come down. So this I compare with the conventional automotive system to the EVs. EVs are also like that because the component of electrical has come. That is going to reduce many others, requirement of other parts. The spring used to be there, spring has to be wound. It is not required now, battery is there, right? Medical and healthcare is a big sector. Dental implants used to make caps, invisible aligners, and implants, mandibular and maxilla, orbital, cranial plates, whatnot. All these are bone. People have been replacing it like no one's business. It is like it's going on for a long time now, and soft tissues are being done. I will not go deep into this because I know people are going to address this. Construction, architecture, restoration, renovation, all these are there, which require a very large system. And people have machines like Massivit and all. They have got a thing which can be deployed. Whole 3D printer is on a gantry crane, and they just come and they assemble the printer there and print the whole house or architecture, whatever. Consumer goods and lifestyle products are two big buckets. Consumer goods, you have today many things. Everything is a consumer goods. People starting from a custom toothbrush to custom buttons to pens to many things. Spectacles, goggles, mask for swimming, hat, everything can be done. And lifestyle products, there's no uh, jewelry itself is a very big thing. Artifacts, custom game products, toys, um, then education, um, um, educational entertainment products, for example. You can have a lab in a box, so that kind of things, it has a lot of capability. Only thing is, when I used to be in Imaginarium, we have made deep inroads into every sector possible, pushing the boundaries of the application, right? If somebody comes with you any problem, we'll never say no to them. Okay, and on a product, you learn how to do it, and you push the boundaries thereby. You failed in the beginning, later on you succeed. Education and research is another big area. Just now I said edutainment. There is a lot of possibility. Mathematics, mathematics, how it can be taught. Children cannot understand abstract things. The moment you have hand 1, 2, 3 like that counting, they can see and count. Apple they can count, but one in the head, wow, 10 in the hand, they start one in the head becomes abstract. And when that is replaced by algebraic terms like x and y, a and B, children have big problem. So the many designers are working on education, how to bring the abstract thinking into children so that they love mathematics, coding, etc. Research also. Research is something, um, the very name says it can be anywhere. It could be in musical instruments, it could be in medical, it could be physics, chemistry, mathematics, it could be in bio systems. It could be in any area. It could be even in archaeology. It could be in anthropometry. It could be in legal, social sciences. You may wonder how. No, all these people are using 3D printing in all these areas, as I mentioned. And coming to energy and heavy industries, it's a very big, what I can say, the depth is so high. You know, when we say heavy industries, it is ship's hull, you know, ship's engines. Some of these legacy things, if they are not made, if somebody has shut down shop for any reason, after COVID, you have to get it made. They are also quite complex. So one off, as we discussed, one off can be made by additive manufacturing. Uh, But when we say all this, we should be very careful. 3D printing, if you have, you should not think of making everything and anything. It should add value. It should improve on. It should better than what was earlier. Supposing you have a better method already in place, which is conventional manufacturing wisdom, don't have to use additive manufacturing. So before you print anything, please ask this question. Because I have a 3D printer, I want to print anything? No, that is not the point. Why am I printing? What I'm trying to solve? Is it good? Or I can do it by many other easier way, cheaper way. That is important. That's where many people make a mistake. R&D में काफी लोग बोलते हैं okay, I can do all this. Nut and bolt I can buy 3D printing, but nut and bolts are available for kilo per thousand is available. So why you want to 3D print it? 3D printing will be costly. Suppose you make a small device which can save somebody's life, and it is going to cost you 2 lakh, then you will be happily be able to give. That is important. So in energy also, you have many things. Generators are there, transformers are there. Uh, they have a lot of energy which is going to transform from one form to another. So there is a heat radiation. This heat has to be managed well. Radiators and radiator efficacy depends on the surface area, and surface area can be enhanced multiple hold by lattice structures. You know, and so that's where I think people are using heat exchangers, and in heavy industry also, in a place where you can combine many functions, make them simpler, more reliable, and that is very important. Sorry, I'll have some water. So challenges hindering the adoption in industry. What are these challenges? So challenges are listed here. You all know. Uh, Again, we'll recollect material limitations. You cannot get every material that is found in nature. You know, it is not possible. They have to be usable by a system, a 3D printing system. It can be molten or applied. You know, they can be cured by UV light, or it can be melted by a heat and extrusion method, or it can be applied like in material jetting, or it can be put together by adhesive. So without this consideration, we cannot have any material that is possible. You know what you think of. So there is a limitation. Then surface finish and post processing is another important thing. Not everything you can finish. Sometimes inside cavity, cleaning is always a challenge. A conformal cooling channel which is there inside, which will have a staircase effect, however small the layer thickness is, that has to be very difficult. You know, people have been trying some uh, ferrous liquid, ferrous media and all, but it is difficult. It is not easy. Quality assurance and certification. Quality assurance means it is not about the drawing and it is adhering to the dimensions. It is not about the material testing capabilities, but beyond that, it will work across number of pieces. Certification. You close your eyes, you use it, and it works. You know, that kind of assurance is also something which people have to have use case capability to test and prove it across several batches, you know. And batch to batch 3D printers have a problem. They are not consistency is not same. Build to build there is a variation today. So they're trying to minimize it, but yeah, there's still a long way. It is like asymptotic. People are very close to it, they're still not able to touch it, kind of situation. Production speed is something which cannot be matched with the depth of cut, speed of cut, RPM. What you have in a CNC, which can remove ton of material by subtractive, cannot be added as fast. That is the beauty of this statement. Production speed is a big problem. Skill gap. If you want to start something, not many people are there. Blue collared people who are trained to that kind of finesse to take care of the accuracy, get a sense of the whole system, and completely in sync. They manage the system. It is very difficult. Skill gaps are many. People are not finding it, lucrative to get trained and wait. So people are getting trained every time a new system is bought, and there's a learning curve. Until they come to some level, the gap will be there. Intellectual property issue is something, you have a product, you scan, and the CAD is in front of you, and you can do anything with it. And so you can modify it a little bit here and there, and so it becomes a new design. That means people will have a issue with intellectual property, in future. Suppose I have a part which is broken. Now I am going to locally make it by 3D printer and attach it. So what happens to the warranty? You know, who gives the warranty? Spare person who supplied spare, or the original OEM, or original OEM will have a digital spare and you can order it. It could be anything. So uh, people are coming out with a lot of solutions. Like then there is a Leo 8, limited edition object. Leo 8 is coming to secure the files. A file can be given with a metadata, that it can be a CAD, which is only plastic, for plastic printing. You can actually give, a kind of a, it'll piggyback on the main data and controls it. Okay. A Leo 8, what you call limited edition object. And so they attach this metadata so that they can have some kind of a control. But these are all getting, as we are discussing, developed today. Some are deployed already, some are getting tested, some have been there in mainstream. All these things are happening, as we discussed. High capital investment. You know, in order for a cheap 3D printer, you can build it for 10,000, 15,000. The Ender and all, riprap mission, you can. But these missions, please understand, they work fine for one day. You can build great parts, but the second day they don't work. Why they don't work, you'll never know, because variables are too many. So when you fix all these variables in a controlled environment, the R&D what you have is quite enormous. A lot of people work, they test it for a long time, and they build many things. That means they have invested so much of R&D into it. And so this is what makes a reliable, bigger system capital intensive. They take, because the whatever effort they have spent, they have to get it from customer. So they will charge that system very high. Well, moving to, you can see there are a lot of challenges on one side, there are a lot of opportunities on the other. So opportunities like food tech, build tech, toy tech, pharma tech, med tech, edu tech, industry 4.0, robotics, IIoT, IOMT, innovation, mass customization. All these are going to outweigh the challenges. 3D printing is not standardized. Additive manufacturing impacts environment. Equipment and product costs are high. There is no 3D printing knowledge. There is a gap, knowledge gap. Additive manufacturing complicates, intellectual property. See, all this limited material available. All this we have discussed. The same thing is put in a graphic. Future avenues of 3D printing. There are many, and we are going to list them. Multi-material and functional printing. Very important thing. Multi-material. For example, you start with bimetal, you know, uh, copper and nickel, or copper and iron kind of thing. It can become a smart material. For bimetal, you have the thermostat and all. They have their own property, because the given exposure to temperature, one side expands more than the other, thereby making it to sag, thereby controlling a circuit, intelligent. So it's smart. So materials themselves can be very smart also. They are using dental implants and surgery. Uh, there is we call it as 4D printing sometimes. Adaptive materials are there which respond to a stimulus, temperature, pressure, light. It could be anything, sound. Bioprinting and organ fabrication is something which is future, because it is not possible so far. People have been trying, you know, you fake it before you make it kind of thing. They're not really there. God is playing hide and seek when it comes to bioprinting and organ fabrication. Large scale robotic, AM For construction, we have discussed this. Advanced metals and composites. We can have composite with anything, metal, non-metal, and composite. You can have composite of all this uh, uh, across. Advanced, then AI-driven design and process optimization. Can we do this? Can we have a build with minimum support? Again, it's optimization. Can we have a target weight for a thing because you're going to make it hollow? You put the target weight optimization. You have a strength optimization by having the lattice. All these things can be driven by AI. AI is in itself is driven by the data. You know, hybrid manufacturing systems. We discussed this. There is the goodness of subtractive. There is a goodness of additive. How can we combine these two? Get the best of both the worlds. And distributed cloud-based manufacturing, we saw the cloud factory there. And in COVID time, it started. Probably they say it fast forwarded the digitization or digital manufacturing, in a way. And today, whole world is using it, and we have sustainable and circular manufacturing is another big thing. It is the kind of a promise, potential, or I can say it is the aim. You want to be sustainable, and circular manufacturing is nothing but you have cradle to cradle and cradle to grave. Instead of having grave and landfills, you can have cradle to cradle. How raw material can be put back in the circulation as a raw material. Sometimes these things have also limitations because of material microstructure. After many use, one cannot use the same material again and again. There is a limit to it. So within that constraint, how can we make it more sustainable? It's a big, area which needs some special focus. Consumer level innovation and democratization. So if a grandma was making sweater, can we 3D print a sweater? Or she was able to select button and or she could make her own button out of wood. Now, can we make our own button, which is customized, with your own family's insignia? All these things, consumer level innovations can happen. Or can you have a custom kitchen something, adapter, for example? So I think that's where people call it as consumer level innovation, democratization, because you're not dependent on a big factory which will be produced for everyone and you buy it. You are able to make it for yourself with that custom requirement, which are used in the context of use. Very important. So you can see here a demo of 4D, all this um, material which is having a thin section there, having those lines, they fold because of heat. It is made by material, two materials, one which is able to respond just like a bimetal, right? Ethical, social, and regulatory considerations are some of the other aspects which are very important. Some of the important questions we have to ask here: how do we regulate decentralized manufacturing? Who controls it? Who maintains the quality? Who will regulate it is very important. There is no policy for this, from the government or the manufacturing people or in the cluster. There's nothing which need to be formulated. I remember I used to work on this project with Professor Attanu. Sometime back, it was given to FECI, government through FECI. We don't know what is happening there. What are the safety standards for 3D printed medical devices? What happens? Who has to be held responsible? These are some things which need to be also addressed too, because medical 3D printing risk is very high if something happens. it will affect somebody's quality of life and life itself. How should government address weaponization risk? 3D printed firearms. Today we have so much of, you know, terrorism. You know, we hear so many things. White collar terrorism. Doctors are becoming, um, centers of terrorism by carrying out, you know, some of these. Now, what if they can print their own firearms or bombs or things which will mass destruct systems using 3D printing? This is something which is again a very important thing. All over the world, we have to look at children, for example, if they don't have, people who are not majority, if they playfully make something which are firearms or killing missions, how we control it. That's one more thing. Legal framework for digital designs and IP rights, even to prosecute somebody, all these things, we need a legal framework for that also. These are largely, going to evolve as the technology evolves. There is no one simple formula. Many times legal systems are anecdotal, so they have a judgment, they will work on some other, and they move on. I think we are coming to the end of the thing, thinking about the road ahead. The trajectory of AM is characterized by convergence. That is the trinity: material, machines, software, biology, automation. In Industry 4.0, I told you about the holy trinity. So, with software and the target areas, biology, automation, and all, these are all getting together. Its full impact will be seen little later when all of them work in tandem. You know, it is going to be not only just additive manufacturing or retrofitting AM into legacy designs. Even this will happen. Future factories may integrate AM alongside robotics, Internet of Things, digital twins, cloud platform, ushering a new era of intelligent and sustainable production. AM will not completely replace traditional manufacturing, but it will increasingly complement and enhance it. High volume components like nut and bolts, washer, etc., even the street pole, for example, will go into the conventional manufacturing only. They're made that way better, like injection molding, extrusion, machining, while AM will dominate complexity, low volume, customized, mission critical application. You know, so in fact, people are looking at you know extraterrestrial building things in moon, building things on buildings on Mars, or maybe Titan, the satellite of Saturn, which is very much like Earth with a blue sky and all. So people are looking at many things like that. In conclusion, 3D printing is here to stay, you know, and it has its own evolution. It is not, though people thought it is going to make a revolution, while the contribution is revolutionary, but I think it is evolving to deliver value, you know, and it is on its way, you know. So manufacturing reflects a broader shift toward digital, flexible, sustainable production systems, which is design freedom, customization, possibilities, material used judiciously only for as much required, decentralization of factories, putting factories in the load center. I think game industry itself is trying to reshape, having its own ecosystem, building its own ecosystem. The future avenues of YAM: multi-material printing, 4D printing, bioprinting, advanced material, hybrid manufacturing, AI-driven optimization, large-scale construction promise to redefine possibilities of engineering and manufacturing. As the technology matures, barriers related to cost, speed, material availability, certification will gradually diminish. That means it joins the mainstream. Today we are saying it's still costly. That's where it is a big hindrance. In future, I think we hope all these things will be addressed. Ultimately, AM is not merely a method of application. It represents a new philosophy of making. It's a new way of making things. One where complexity is free, customization is standard, sustainability is achievable, innovation is democratized. The coming decades will witness AM becoming indispensable pillar to the global industry, healthcare, infrastructure, and our daily life. Thank you. I think with this we come to the end of the presentation. I would like to take few questions. If Reva, you can take the control.
Yeah, thank you very much, sir. Uh, Very much insightful lecture, sir. Actually, I was listening to you, and how I mean, I'll ask the first question, and then I will leave it to the participant. Okay, because I'm very curious about the few things which you mentioned in your lecture. Um, so, sir, first is the legal aspects you mentioned. How is the preparedness as of now, like about the legal aspects, and in the India particularly, taking if you can take into consideration.
No, it is evolving. I'll give
Okay.
an example.
Uh-huh.
When I had a call from a surgeon way back in 2012,
Okay.
more than 10 years ago,
Okay.
and the patient family thinks I can help them, I can save, but I have no idea how I can save. See the whole thing, and
Okay.
we went on to discuss about a cranial plate, which was supposed to be 3D printed.
Okay.
Surgeon thinks I can do some magic. I can make the cranial plate out of
Mm-hmm.
titanium. Titanium is a very difficult material to work with, you know. And
Mm-hmm.
you may not believe, company was also very afraid. What happens if somebody puts a medical legal case, your
Okay.
implant did not work?
Uh,
So the approach I'm telling, which only as a practitioner I can tell, we wanted to save our skin. you know
okay.
in legal system, first of all, if I am caught by the legal system, they'll first ask you who asked you to make it.
Mm. Okay.
So you should say doctor was there,
Uh,
he wanted me to make it.
uh,
So doctor will ask anything. How do you know you have the capability? Number one,
okay.
where is the proof that doctor has asked you?
Uh,
And from everyone else, why he came to you first?
uh,
What you did, was it tested by doctor?
okay.
So we have built a very robust system around it. It was asking a question: what
Okay.
if the legal system will ask me this question? Getting my
Okay.
point? You
Uh,
know, it is like a kind of a FMEA we did.
mm.
What if it fails, and if I am going to be imprisoned in a jail? You know, what
Okay.
question they will ask in the court?
Okay.
That kind of questions we asked ourselves in
Okay.
order to make. So doctor needs a prescription. We need a prescription that
Uh,
doctor wants something like this. And or I make something and give it to him,
okay.
and he also doesn't know.
Mm.
So will doctor approve it? So
Okay.
at every stage, it
Mm.
is built in a system by asking question: what, how
Okay.
to save my skin? How to save my skin?
Mm.
Got my point, no?
Yeah,
So
yeah,
today,
absolutely.
today we have got ISO 13485, a license for it, and we have a very robust system inside. A
Okay.
system which was built without looking at ISO 13485, 13486, whatever, 13485, whatever.
Okay.
It was not looking at that, because any legal system builds up on a thing like this.
Mm.
Same way people have IPR issues. They have some people copying some things.
Mm.
So how they are able to handle it?
Mm.
So that becomes anecdotal to the next group who are going to address it. So there is a proactive steps people take. You know,
Okay.
and that is shared. For example, my medical thing, I did medical ethics, legal medical. I studied medical law in order to save ourselves. You know, what are the implications? I went through legal system of learning legal implications, actually going to a college and learning those. And my dissertation is there, for everyone to adopt. That means
Okay.
it is important. Such many case studies, use cases are going to help. Legal system works on the case basis. You know, so they anchor on to something like a ladder. Somebody creates something, you build it upon it. Whole research, for that matter, in the scientific community builds on something. Nobody nowadays discovers something new, right? So legal system, I think it is getting ready. They are able to understand now technology, its implications, the capabilities, the good things, and the so-called bad outcome it may come. So how to counter it? So all these things are getting developed.
Okay, great, sir. And now we
Thank
see
you.
in like 3D printing very matured in dental cases. So the legal framework almost being there when freeze was there is something more to come in dental case. Similarly, in jewelry also quite effectively they are using this 3D
Yeah,
print.
true.
Mhm.
Many times confidentiality agreement they have, so people should not. But today I can lock my design. Design will be used one time and it expires.
Okay,
I'll send you a, for example, you buy from me one CAD, I'll give you, and you print it. That CAD you cannot sell it to somebody.
okay.
You cannot copy and keep it because it is going to expire after one use.
Uh, uh,
Suppose one use, the first use, it did not work properly. There is a
uh-huh.
mission failure and
Uh-huh.
half built. Probably there is an intelligence built to allow, or you have to request. See, this is
Okay,
what happened with proof. I will allow you, you know.
okay.
But you cannot fail 10 times and ask me for 10 times you give me, you know. Or if
Mm-hmm.
you are buying for 100 pieces, so the file will be authorized for 100 times. After
Okay,
100 times, it will expire. Or it is meant for 1 year. You can buy today and use it. The file is valid for 1 year. You cannot crack that. It is encrypted. And after one use, it will expire. After 1 year,
okay,
if you have not used it, it will expire.
okay, okay.
And the plastic thing, I can lock it to plastic. Suppose you want to make gold, I will lock it to metal, you know. Or if I'm giving to you only for plastic, and for metal, I'll give additional charges you have to pay. People will buy readily plastic one and use the same model, no? That is not allowed. So I can lock a file for the what input material, what mission it has to run. Such capabilities are there in limited edition object, Leo 8. It is just an example. I'm not a marketing man for Leo 8, but
Okay.
uh, there is another company called Authentize. You can have security. So security encryption is a big thing. Blockchain things, they're all coming in order to give assurance to both the creators and the users,
Okay.
thereby maintaining the warranty class, etc., of the people.
Okay. Mm. Understood, sir. So, and a few one more question comes in chat window from participant Dr. Sachin Kamble. How is cellulose 3D printing useful in AM?
Well, cellulose is something which is bio-based, so it can be used in the um, biodegradable wherever you need requirement. One can use it. It can be used in many applications which are having direct contact with your body, for example. It will have more conducive, contact. breathable contact or absorbable contact, things like that. And in cellulose also, you see, a material when they develop, the properties of these are going to vary. They have to transform it to the 3D printing printability. There is something we forget always. 3D printability has its own what system, given these seven different technology, where it will go, so what it has to do. If there is a transformation which will spoil the basic nature itself, then it is not good. So it all depends. So cellulose, you can think of many applications. It could be even used in packaging. It can be used in biosystems. It can be used in making clothes. It can be used in exoskeletons and many areas you can think of, because it's a bio-friendly material. Hope I have clarified.
Hope
Thank you,
Dr.
sir. Thank you,
Sachin
sir.
you got it right. And one more
Thank you,
question, I
sir.
think
Thank you,
Raj.
sir.
Yeah, Dr. Sachin, you can continue.
No, no, I have understood each and everything, sir. Thank you, sir.
Yeah, Dr. Rajendra, you can proceed with your question. Dr. Rajendra Verma. Dr. Rajendra. Okay. Any other questions from the participants?
I think he has muted himself. Rajendra has
He
muted
raised the
himself.
hand, Dr. Rajendra, but
Now you
Dr.
can
Rajendra,
ask.
you can unmute and
Now he has unmuted himself. Dr. Rajendra.
Dr. Rajendra. Okay. Any other questions from the participants? Please feel free to ask. Any questions, please?
Shazia Anwar.
Yeah, Shazia.
Two hands
Sir,
up actually. Rajendra
good
Verma and
evening, sir.
Shazia.
Yeah,
Good
good
evening.
evening, sir. This is Savi Anwar.
Yes,
Thank you,
madam.
sir, for giving the chance of asking a question in this. Sir,
My
actually, there is
pleasure.
a very misconception. There is I have done a workshop on 3D printing this last month. Like we at Hyderabad Usmania University, we have two additive manufacturing centers. So we have machines from Israel companies and all for SLS and SLM companies. The
Hmm.
conception is that 3D printing and the additive manufacturing with rapid prototyping, there is always a misconception. People are not able to understand. We say 3D printing. We, being mechanical engineers, we say it as additive manufacturing. But commercially, it is being used as the word 3D printing. So I just have, my doubt is very small, or I don't think so. That is might be stupid also. But the thing is that what is the actual way of representing this technology? And we know that this is going to be the advance of mechanical engineering. As now everywhere all over India, the mechanical admissions has gone down. We are not into that hype right away because of the all AIs and everything. But we know that I have this confirmation that additive and as well as robotics are the main advancements in the mechanical. So, please, can you give me any idea on this?
Okay. It is very
Thank you.
interesting. Today, I wanted to keep it very advanced level presentation today. I've not included many presentation here, graphics which are meant for college students and all, small children and all. I always say 3D printing is not one but many different technologies. They're called as 3D printing. Okay, it is like how elephant is felt by blind people, a group of blind people, as something which is like a pillar, something touches the trunk, they call it as a rope, like that. Somebody thinks it is a wall touching at the stomach of a elephant. So 3D printing is also like that. There are different technologies, but we call all of them as additive manufacturing or 3D printing only. Now coming to rapid prototyping, we can actually see a kind of a chronological timeline here. Dr. Kodama, when he first discovered it, he called a rapid prototyping. That was used for a long time. Even during stereolithography, they called it as rapid prototyping only. The purpose was rapid prototyping. Okay. So it was for a long, in the beginning, it was called rapid prototyping. Then when they suddenly stereolithography also means 3D printing. Stereo means depth. Lithography means printing. So stereolithography is nothing but 3D printing. Okay, but they never called that way. They also had a beautiful word, stereolithography. It's a very nice word name, for technology. And 3D printing was itself was trademarked by binder jetting, discovered by MIT. You know, and the Emmanuel Such was the person who was the professor who supervised that project, and they trademarked it, 3D printing. But the whole world took that 3D printing, as a buzzword for all these technologies. Then they had to give up their right on that so-called trademarked name, 3D printing. Much later, people started calling it as additive. For me, additive is a wrong, kind of a misnomer. Additive, we should not say additive, because for me, additive is a larger umbrella, right? Larger umbrella, because under additive, all things will go. Adhesives will go, welding will go, cladding will go, plating will go, gluing will go. uh, our buildings are made additively. Bricks are all put, like a Lego, we put together. Build a wall, build a building, right? It is additive. Laddu is made into in bundis, but it is having a shape and all. But it is additive, not 3D printed. So additive is the larger umbrella. 3D printing comes as a subset of that. That's what I, as a practitioner, could literally say. But as a practitioner, I will say it is a digital fabrication, is the right name. Digital fabrication from a digital data, layer upon layer. Now, layer upon layer also has gone because they have used the robots to hold some kind of extruder. It keeps on extruding, and they are able to write a cuboid, using, they are able to make a cuboid, a cone. You have seen that, some animations, because it is not meant for students, are not included here. But you can, there's no layer. You're able to write something vertical, it stays. You have one more writing, it makes a three, it makes a pyramid, right? And all these are not having layers. But one thing is there, it is not 3D printing because data is coming from your head. A 3D doodler that way is not a 3D printer, though it looks like a FDM. It works like a FDM, right? And so somebody is asking a question. In the meanwhile, I'll take it. So it is allotropic form. I will say they have allotropic forms. That means occurrence in different forms, right? So additive manufacturing, 3D printing, rapid prototyping, digital manufacturing, and uh, digital fabrication. They're all same. Hope I've answered your question.
Yes, sir. Thank you. And
In
Thank you,
net,
sir.
you will actually
yeah,
find a diagram where I have put it as elephant, blind people touching. That diagram you will see. I have not included here.
yeah.
Yeah.
And next session speaker already has joined, but I will we will have two more questions, sir, from the participants quickly.
Please.
One is the Dr. Makarand is asking, can you explain more on the 3D 4D printing, and Professor Swapnil Mahajan is asking, like, can we print alloy wheel using 3D printing? So quickly we'll take these two questions.
Alloy bell.
Alloy wheel using 3D printing, can we print it?
Alloy bell. Okay. Well, I think today the first question was about what?
4D printing. 4D printing.
4D printing. Okay. 4D printing is actually there is only 2D printing in the world. Let us understand there is no 3D printing in this world. You know, when 2D printing is done again, again and again, you get a thickness, and that has become 3D printing. Now, 4D printing, somebody calls it, is also 3D printing only, or it is also 2D printing only. Only thing is, if you are able to print two different material side by side, then if they act to a stimulus, temperature, pressure, light, or sound, whatever, then there is an action, there is a kind of a um, actuation that happens. Then we term it as people. We means that not me, the community, or that small community which worked on that area. They call it as 4D. People also call it 5D. 5D means if you are going to have a rotating drum or a rotary thing, and you have one more dimension added beyond fourth. People say 5D printing also has come. So for me, these are all marketing jargons. That's all. 4D printing is nothing but 3D printing done with smart material. The smart need not be, it can be dumb also sometimes. Bimetal is also smart. The way it works as a thermocouple, thermo stat, it is smart that way. So as long as they can shrink or expand, uh, it can lead to some kind of an actuation. Compliant mechanisms, for example, they're not smart material, but they work smartly. The spring is not there. There is a element which acts like a spring, you know, and so the part count becomes one. So high reliability. So like that. So 4D printing is something using smart material and normal material together in order to have a transformation. It could be a small or a large relative expansion or contraction, which further is fulcrum to get what you want. It all depends on how you put them together. That is very important. Hope I have answered your question, sir. The other
Yes.
question was about um, what was it about? I forgot. Sorry.
Can we print alloy wheel? Alloy wheel.
Alloy bell.
Yes.
Alloy bell. Okay. I think it's possible. Alloy bell. Alloy only you take. You take alloy only, because if you are printing FDM with ABS, ABS is also alloy of acrylonitrile butadiene, styrene, right? ABS is an alloy in polymers. Metal also you can have as long as it melts. So wire based FDMs are available where you have a wire coming out, and you are going to heat it with plasma, and it drops down. It's called drop on demand on the platform, and you move the table such a way that there is a string of such drops coming together, making a layer of it. You know, so there, whether it is tungsten you're feeding or you put alloy wire, copper, whatever, it works, right? The other way would be sintering, because it is all made up of particulate matter. If you have a even distribution of these particles, and then you sinter them with a laser, that is laser bed fusion, then also you find the structure made up of these two. At a microstructure level, how it will function, I don't know. But I think alloy wire have been used successfully. People have got some good results. Bell, I'm not sure, but I happened to make a bell for a small train, toy train, for Dr. L&T HR head, Dr. I forgot his name. He's retired now, but he makes the small trains, and he wanted a bell to be made, but this bell doesn't make noise. It's only appearance as a bell. Okay. So bell metal, well, why not? Multi-material, functionally graded materials can be used. Okay. Either you can grade it structurally or material-wise. By then, with the play of this, it is possible. In fact, there are bimetal printers available in the market. You contact me directly, I'll give you details of those systems.
Okay, thank you, sir. There are many three, four questions, but I think
You
already
can mail me,
we entered into the,
I'll be
yeah,
glad
I
to
will mail
respond.
you all those questions, and then
Yes, yes.
I will
I'll be
direct
happy
the
to.
participants also.
Yeah, yeah.
Because already the second session.
I may not have answers for all of them, but
Uh,
I'll
uh,
try to answer all of
no,
them.
but you elaborated
On
a lot way in much deeper way, sir, and so many questions. It really the acknowledgement to your depth and how curiosity you have generated among the participants.
my pleasure, sir.
Yeah.
And it's
So
all learning together sessions. I'm happy to co-create. If you have any research problem, I'll be
yeah.
happy to give my view of it, or
Okay. Mhm.
collaborate with you.
Yeah.
I'm
Yeah.
looking forward to collaborate with all of you.
Yes.
Thank you.
Yes. Thank you. I'll share in case if you permit your contact details and email ID to the
Sure.
participants
This
so that
presentation
they can.
also, I'll enrich it and share it with you all.
Yes,
Okay.
that will be the great help.
These are nothing. Nothing is copyrighted. It's all for
Yeah.
education,
Yes.
and we'll push the boundaries of knowledge together. Thank
Yes.
you.
Thank you very much, sir. Thank you once again
Thank you.
from the Sardar Patel College
Thank
of
you.
Engineering and from the AICT ATAL program. It was really the wonderful platform that you have set for this particular program. Thank
Thank
you,
you,
sir.
sir.
Thank you very
My
much.
pleasure, sir. Thank you.
Yes. Thank you, sir. Okay, and then already we are into the second session, and our the expert for the second session, Dr. Datta Parle, is on board, and let me take this opportunity to welcome Dr. Datta. So, Dr. Datta is the technical fellow, robotics, AI, and automation at AMRC Northwest United Kingdom with 25 years of experience in advanced manufacturing and emerging technology. Dr. Datta is almost, in his career, touch upon the various sectors such as aerospace, automotive, defense, oil and gas, energy, heavy engineering, nuclear engineering, biomedical engineering, etc. Datta Parle was associated with many organizations like BRC. I think Datta, you started with BRC first job, and then the Infosys, Wipro, Geometric, where he won many prizes also, and then Nuclear AMRC at UK. Dr. Parley has influenced over 15 million US dollar in project and proposal revenues and has received several awards and recognition for technological innovations and engineering excellence. His strengths span product and service innovation, partner ecosystem development, high-profile client solution, compliant management, and quality-driven engineering solution. So I'm very pleased to welcome Dr. Dattatray Parle here for this AICT ATAL program for the second session. Over to you, Dr. Datta.
Thank you, Dr. Kiran, and thank you for inviting me. And nice meeting you online. Since COVID days, we have not met physical, right? And maybe when I'm there next time in India, probably I will certainly try to meet you. I'm not sure how the I'll share, but let's see whether sounds of video will come. I don't know. Is that visible, Dr. Kiran?
Yes, yes, it's perfectly visible,
Yeah,
and you
yeah,
are audible also
yeah,
very well.
yeah,
Yeah.
yeah. Okay, thank you, Dr. Kiran, and maybe further participant information, myself and Dr. Kiran were doing PhD together at IIT Bombay, and since then been
It was wonderful.
yeah, since then been our journey started, and we try keep meeting on various forums, and this is one of the forum where Dr. Kiran always try to involve me into some of the other things of Sardar Patel. Thank you, Dr. Kiran, for your and once again, today I will try to take you through one of the interesting topic, interesting research which we have done, and maybe some more knowledge on 3D printing, some specific knowledge on what we do in our research center, more focused on expanded horizons of materials for 3D printing. And one of the major part of my presentation, I'll talk about one of the PhD student who worked on creating new material and then doing a lot of experiments, uh, which is a different kind of material. We tried creating for low cost 3D printers and specialized applications. So I have planned this in this manner. I'll maybe brief introduction Dr. Kiran has already given. I'll just go over it and then give some brief introduction to 3D printing. And one point of time, I was doing a lot of product designs and manufacturing using 3D printing, more polymer based plastic. And then I'll go into the specific details of today's topics on materials used in 3D printing, what are the challenges, and then the more focus, the one of my PhD student, as I said, who worked on to whom I was co-supervising, and it was mainly manufacturing this particulate composite PLA for biomedical application, and what we did, what are the research outcomes and all that. And if time permits, I work now at MRC Northwest, which are the state of art 3D printing machines. I can't talk a lot about their project because more of those projects are some defense related work. So, but I can tell you what kind of machines we run and what are their capabilities and all that. So then we'll do some concluding remarks. Let's see how much we can do, but maybe I won't stretch you much if because it is too late in India, I know. So brief summary, like maybe 2 decades now, industry and research mainly. But I'm associated with a lot of academics, like through people like Dr. Kiran. Every most in Mumbai, Pune, Maharashtra, major part. I'm involved with a lot of the institutes, delivering some lectures or participating into the. I have been uh, uh, I have been doing a lot of different works in my career. Primarily, early career I did more into CAD, CAM, CA, and all that, and then later on, maybe last 1 decade, more focused on emerging techs like Industry 4.0, digital twin, additive manufacturing, VR, AR, autonomous vehicle. Then I did my nano degree from UDA City as a self-driving car engineer. Probably that's another future technology. And I was also a major part into the software development. I participated across the product life cycle, works, different customers, concept to manufacturing in various aerospace, major part aerospace, automotive, nowadays a lot on defense, but not defense our country, but defense of UK, oil and gas, uh, energy utilities, nuclear, early career, I was there. And when I shifted UK again, I was into the nuclear research center, and then biomedical. A lot work did in the middle on biomedical engineering. So I had been in most of these Infosys, Wipro, and those companies I have been, or even now, we have been trying to do R&D led service offerings in different areas. Currently, it is more on AI automation focused for manufacturing and defense sector, but earlier it was more diverse. And some of the part which comes, maybe I might talk, is based on what I used to do in those companies, and that's what tried creating some of the products in my own startup in India. So let's start probably the this is one of the, when I used to deliver the 3D printing lectures, I used to bring this slide up. So there are there is one common thing into this all five six pictures. So now maybe if you see here, there is this some logo, some my daughter's school logo when she was in India. There is this electric board. That, then there is some casing for Raspberry Pi. Then this is a kitchen. Then there is this paperweight, and then this photo from my bathroom. Okay, so all have one thing common, is a 3D printed thing. So this is a 3D printed. This is a 3D printed. This inside this lotus is a 3D printed. The bathroom attachment is a 3D printer, and this kitchen was 3D printed. So a lot of things I was doing a lot one point of time. Maybe these days I'm not doing a lot. I'm more focused on AI side in artificial intelligence. So today 3D printing, I say, is it is made as easy as a paper printing. If you are looking for a low cost, I'm not talking about the industrial printers. If I'm talking about the common 3D printers, it is I just compare it as a, if you look at the shape size of the low cost printers, paper printers, they are comparable today. And the way 3D printing works same way as a paper printing. What we do in a paper printing, we create a document. Just we open, let's say, doc file, write something, send that file, and then you just get a hard copy of it, right? Same way, if you know a bit of a CAD, create something in a CAD, send it to the 3D printer, get that part ready. So that's how it works. So today's 3D printing, and even if you look at the industrial printers, also work will similar, but there involve some complexity in terms of what kind of material you handle, toxicity, temperature, maintaining those parameters, and all that stuff. Other challenges, like maybe we might have industrial, but as a common man, if we are looking at the 3D printing, is that as simple as that. So it's as good as a paper printer, right? So maybe I'll pray. I don't know. That's what I was thinking. Let me know if this video sound will come.
Understand how possibly it's going to change the various.
Is that audible, Dr. Kiran? No, right?
Yes, it is audible.
Yes, sir, we
Audio.
could hear.
Okay. Good. Yeah.
Industrial sectors, global economies, and also our lives. We bet you're thrilled to hear that. So let's get started. What if? What if you could print your pizza in your own favorite shape and then have it for a meal? What if you could print spare parts for your grandfather's antique car and have it fixed for him? What if you could make your own custom-made objects at home for your loved ones without paying extra charges for the customization? What if you could build your dream home in a shape as complex as you want without compromising your aesthetic sense? And what if you could save the life of your loved ones by replacing a damaged organ with a 3D printed one?
So, I mean, this is the reality. This is going to be the future. This is what happening. I mean, just to give one, before I shifted UK during COVID, and I was looking for different kind of jobs in the research center and in the companies, and applied. And I thought I will also try, you know, postdoc, and I got one postdoc which I really did not accept it later in a biomedical medical 3D printing. So there is a lot happening, and that's what you can see the future, and is going to be there. I mean, 3D printing is there to create some magical things in future.
Stand.
So maybe I'll quickly go into, maybe you will hear this again and again, but I'll quickly try to jump into. So manufacturing, it is a manufacturing process, right? There are several manufacturing processes, and we have been, as a mechanical engineer, we have been studying this farming, costing, machining, and powder metallurgy, and all sort of different kind of manufacture, welding, all that, right? Now, since probably 1 decade, we are going to we are hearing a lot on 3D printing, or alternatively people call additive manufacturing, and but this is not very new. Earlier also it used to be there, but earlier, when I was doing my masters in IIT, it was there, but I didn't realize it is a futures additive manufacturing. So there are various subtypes. We'll go probably later, but yes, what we probably do is I mean, the way that we call it additive is we add the material. I mean, it is a addition of the material instead of, removal of the material, or changing the shape of the material or something like that, but we are adding new material in some or the other ways, and that is why it is called additive manufacturing. So additive manufacturing is a process of uh, making, as I said, 3D models, like, as I said, hard copy of your uh, models, CAD models, and it is done by adding the materials. That is why it is generally called as additive. And maybe alternatively, this 3D printing has become very popular name in a common man's life, but additive manufacturing is a more scientifically accepted terminology in the ASTM standards. So maybe technical community might only refer it as a additive manufacturing, whereas common people might still call it as a 3D printing, or maybe a 3D printing is more synonymous with the polymer based printers, uh, and maybe for industrial manufacturing or metallic manufacturing, additive manufacturing is a more accepted or used terminology. But you take any, whether it is 3D printing or additive manufacturing, it is additive process. The way of additive, the process of additive material is a different in each different common plastic machines or industrial machines, but it is again the fundamental, it is same. You are layer by layer adding the material and to get that 3D form of the shape. So there are a lot of applications. I mean, one of that earlier video you have seen, where you could see there are several applications. I mean, biomedical is one heavily investigated, and today I am going to talk about one of the research which is very applicable for a biomedical, and then automotive, aerospace, architecture, consumer goods, education, everywhere. So maybe you might be hearing stories these days. Oh, somebody has constructed house using 3D printers, or somebody has constructed some automotive parts using 3D printer, or somebody has manufactured aerospace parts. So it's not novel now, because more and more development is happening in this world. A lot of uh, applications are increasing, and so maybe there is a brief video.
You can
Let's
almost create or print anything and everything using a 3D printer. So let's take a look at a few of the applications where this technology is currently being used. Where are we now? Today, 3D printing has found applications across various sectors and has helped these sectors by making it possible to create objects that are costly or difficult to produce using traditional manufacturing techniques. In the automotive field, German automotive manufacturing giants like Audi have been using 3D printing for quite a few years now, and as recently as 2017, they started their own 3D printing center in Ingolstadt. Audi uses 3D printing for manufacturing spare components with complex geometries, which are otherwise costly to make, considering the low volumes that are produced. However, the use of 3D printers is not just limited to the making of the spare complex parts. Now there are several startups like Divergent 3D that are prototype testing 3D printed cars. These startups have at present successfully created car frame bodies and chassis using 3D printers and are aiming to develop entire cars that can be 3D printed. Considering the nature of this technology, 3D printing helps to eliminate the waste and pollution that's created by factories and will not only change the automotive sector, but the entire manufacturing sector in the coming years as it advances over time. In the field of medical technology, a lot of research has been taking place to explore the opportunity of creating 3D printed organs that could be used as a substitute for organ transplants. Once fully functional, this technique could help doctors to create organs and tissues compatible with a specific patient's anatomy. And Luxers, if you'd like to know some more about the advancements in the field of medical technology, you can check out our trends video, Survival of the Richest: How Long Until Billionaires Can Live Forever. In the field of construction, Dubai and China, who are considered to be construction giants, have been working on developing 3D printed houses and skyscrapers. In fact, a company in China has claimed to have built 10 houses in 24 hours using 3D printed technology, whereas Dubai is claiming to build 3D printed skyscrapers by 2030. Such applications in the field of construction will not only help in cutting down the manpower costs and inefficiencies involved, but also make it possible to build complex structures in shorter time and in a cleaner way. 3D printing is also disrupting the food industry, and 3D printers that can be used to print food have already been prototype tested in England. These 3D printers can be used to create food like pasta and hamburgers in your favorite shape, and all you need to do is cook them in a microwave once ready and eat. Sounds kind of fascinating, right? Some of these food printers are also available for sale, and you guys would be delighted to know that one of our favorite fast food giants, McDonald's, has announced it would be selling completely 3D printed hamburgers called McMac by 2020. We can
So that is a brief. I mean, those again videos were old. I mean, this lecture more than 5 year old now. So going into the history, so I still remember. I mean, 80s and 90s were still infancy days, and I completed my BTech B in '99, and I joined IIT Bombay for my master's program. And there was a professor Karuna Karan who used to do this rapid. There used to be a one. He has developed this layer by layer deposition machine, and that time we used to call rapid prototyping. And I mean, if I have to be honest, I remember I never. It was so slow process. I don't know. I mean, I used to think, is this going to happen anything with this in future? And maybe 20 years later or 10 years later, probably I was wrong. And that is the most talked process today. That is the most talked machine which he used to demonstrate and teach us during that day. And that's then probably the early 2000 had changed a lot and made a lot of progress. And since last probably one decade, 2015 to so today, it's a tremendous. And the research center where I'm working, although I'm not exactly the part of the additive manufacturing group, I'm more into the AI and automation for all the groups. So, but we have state of the art are the world's largest industrial 3D printers, and that's the you can imagine now. And we are trying to create most complex parts for aerospace, defense, and automotive sectors. So I'll not probably go into the too much details of this. But, I mean, maybe I'll share this deck, and Dr. Kiran will circulate, and my email and phone numbers. Though although my phone doesn't work, but WhatsApp works in UK. I'm currently in UK, and my email is also given. Feel free to contact if you have any questions. So maybe just I'm taking a step back. When I was just during the COVID, I was doing a lot of 3D printing, and people use this for a variety of purposes. I mean, people started creating. That's why I said, right, maybe they were trying to create this kind of hooks to avoid infectious diseases and contacts. And I also tried creating, and if the process is simple, right? You create this 3D model file, CAD file, send it to the 3D printer, remove it, clean it, and use it. And I did a lot of my own products, maybe for personal use. My wife is a doctor. She used to run the clinic, so we created this 3D printed soap dispenser. We also created this lightweight, ultra lightweight, full covered uh, face shield to protect Dr. Moore from the contact, and see what kind of using for her own. I mean, we did not really make these commercial products, but that's how we started using the 3D printers, and for during the COVID. And that time I had my own startup simulation center, I used to call it, and I used to do a lot of different things. And one of the first thing I during that process of 3D simulation center startup days, I created a lot of products, lot of 3D printing products, and all of those were available on Amazon. So some of these are here, many of these I have probably not listed. So I'm maybe I was working on one of the another technology called VR, virtual reality, and then I created those VR headsets, lot of different type of VR headset forms and shapes and all that. And maybe for Christmas, some Christmas customized, maybe for I mean, the first VR headset we created was tricolor shape, and these are the all different mixed colors. And one good part of this 3D printing, all was done using a lowest price 3D printer, that's a Ender 3. And a lot of research and play I used to do with that. And all these are jointless. This is a complete one piece product, no joint, no color, everything. I mean, even we did some DIY kits of the same headset. Then we created this is something called VR selfie. Then I was also trying to design these filters for for those COVID days, right? For doctors again. And this was one of the popular game on Amazon, Pac-Man game, 3D printed Pac-Man game. It was very popular. Unfortunately, I had to stop that and come shift to UK. And then I used to also just started some experimenting with. But so this is a DIY kit. You can make this, you know. So a lot of that I did 3D printing, and this is how I used to. So you can see this is a jointless with the, I mean, the single filament, but we still used to manage a multicolor with a lot of different ways. And we used to successfully manufacture it a good strength VR headset reasonably without any assembly required for this headset. So and this was probably maybe let me see if this video works. Kit from Simulation Center to make a more durable VR headset. This is what you will get. So these are the parts. This is the base plate, top plate, flap, lens plate, side plate, splitter, lens holders, lens, Feviquick, and this is
plastic rod. I call it noodle. And now
So I'll just show you maybe these parts using. We used to create a VR headset, and that VR headset
it's
we
true
can just
story.
put,
If you want to see even
and
elastic
then
band,
you can use it. And we used to play a lot on this because I mean. Uh, we used to do a lot of experiment with this because the way you print the 3D part on those machines has its impact. So, and that's how that my PhD students research led to that my experiments with this machine, and then we did a lot of research to that. So let me, and then there were some. Then we started some doing industrial products and all that, and then COVID started, and probably we stopped. I did not do much later. So one point of time, I mean, I was Amazon entrepreneur, I call. I mean, I used to create a lot of 3D printed products and sell it on Amazon. And that is something I thought I'll base, that was a base for my what research I did later. Couple of students did, I was co-supervising in India. One was from Uttar Pradesh, one was from Pune, and again two different topic. One was in artificial intelligence, one was in. So I'll be talking more on, and then here also after coming, we started creating our own, just for using it for our own in-house 3D printed VR headset for virtual tours of the facilities and that like that. So for that, my VR headset, I got some recognitions. A business standard published article, not for this 3D, it was not for 3D printed, but because I created the VR headset of 200 rupees. It was the lowest price worlds. And those days, I'm probably, maybe now I am talking about the 2017 or 18, 2017, and it's 7 8 years now. And those days VR was very boom like today's AI, and the VR headsets were costly and all that. And then I did some led some VR services based businesses in Infosys, and after leaving the Infosys, I created this cardboard VR, and then that changed everything. And later on, once I was successful making that popular and selling it on Amazon and various places, then I created. Then I because I did 3D printing some work in Infosys, where we were trying to create the strategy how existing parts in aerospace and automotive can be replaced with 3D printing and all that. And then that's where I had got some additional knowledge of 3D printing. Although, as I said, rapid prototyping by Professor Karunakaran was one of the first learning, but I never thought that someday I will use that. And then I created first 3D printed VR headset I created was a tricolor. And this tricolor, the good part, and then this was demo in 2020, just before the COVID, there was this Maha Expo in Aurangabad, Maharashtra. So I demonstrated along with, by collaborating with one of the local engineering college in ICIM engineering college in Aurangabad, and where it was given a best innovative product award. That because one of the part is it was so sturdy. I mean, it's very strong. Uh, Created using low cost 3D printer, that's Ender 3, probably, if you see, right? And which has no, multicolor, but we tried successfully creating multicolor without joint, single product. That was the probably the novelty, I would say. And this was the printer we were using those days, and we created a variety of those products what you have seen. So this is a called a FDM 3D printing. Now FDM 3D printing, the way it works is probably I'll just this probably you may know, many of you know this. So it is a uh, it's more like a structure like a three-axis Cartesian robot, right? And then you have this filament spool which is melted and deposited, that there is a program running to deposit uh, this material and move this motors are there to move in x y z directions and all that. That's how it works. And then you can do this control, I mean, essentially it runs on the G code, which if you are familiar with NC programming, then you will understand. And that's what we used to do. I used to do a lot of experiments with that G code to get what we wanted to get in through these low cost 3D printers. And that's how then a lot of I started interaction with the industry and a lot of interaction with academics, and that's how two students started doing PhD with me, and I continued even after coming to UK, and that is how it became the I mean, one of the philosophy which I was trying to run at simulation center was, I mean, we won't do the prototyping. I mean, often today also people talk 3D printing as a prototyping, but we said we'll create directly the product product and using directly 3D printing process. And we started doing more simple products. I mean, this was my first cardboard product, right? And that cardboard product we converted into 3D printing. And then we started looking at different products. And this is one of the topic I'll do today. I'll talk about what we did, what kind of novel biomedical application we did. So it's a complex, so this was a product which we first made cardboard using 2017, if I exactly remember the year, during the, and this was the Diwali time. During Diwali time only I launched this product, and we got a largest order from SL World, and this product become kind of regular product. And once we have successfully made it, we converted into the then we created a DIY kit of this. After DIY kit, probably we created this version of the product, I mean a plastic version, the IGTs. And then we thought maybe we will create a DIY kit. So it is the process is simple: concept, develop, launch any product. So these are the parts, drawings, CAD parts we created, and we printed, and we created the product line. So in plastic, I mean, I was doing a lot those days. I mean, one time it was like, oh, anything you need in plastics, I won't buy in my home, I will make. Okay, that's the philosophy we started adopting. And it's the now case, probably in future more and more plastic parts might be 3D printed, and because materials will become cheaper, possessions will become cheaper and all that. So and that is, you may see more and more this available everywhere. So this is a FDM, where fuse deposition modeling, but there are some advantages as with disadvantages. FDM is the most cost effective today because for the thermoplastic parts and prototypes, but wide range of thermoplastic material is available, and there are different kind of materials available. Probably I ended up, if I did not really calculate, but probably I might have used almost uh, 200 300 kg material, plastic PLA and primarily PLA, and maybe some amount of ABS and other during those my startup days. And maybe PLA, this FDM has low dimensional accuracy and compared to other 3D printing technologies of industrial scale. But there are several challenges because of the way it works, right? And then post processing is required, sometimes adhesion, and we that is how the one of the PhD student came up with this, because of looking at these challenges, because we don't know how do we print. We have to do a lot of experiment first, ensuring repeatability of the product. We had to think, oh, whether we should print vertical, horizontal, all that. So these are the another challenges. So Maybe I'll talk more about the challenges of those 3D printing later, and that's what it led to. But maybe quickly, there are, if you look at ASTM standard, these are the 3D printing types, and I think earlier speaker was talking about many of those, right? Binder jetting, DED, material extrusion, material jetting, powder bed fusion, sheet lamination, wet uh, polymerization, and all that. So each one has its own way of working, how it works, maybe how you dissipate the energy, whether you melt the material in a powder form or in a solid form or what, right? So it at different ways, but essentially it is adding the material layer by layer. So everything has probably, or solidifying the material layer by layer in the powder form, all that. I will not go into those details because I have a lot to talk on my specific research, right? So I just wanted to say that is why ASTM standard talk says more of additive manufacturing as a legal term rather than a 3D printing. 3D printing is, although 3D printing, printer and printing is more equipment side of word they consider, but additive manufacturing is a commonly. That is why I said maybe a more common people might say 3D printing, but industrial sector you might hear of additive manufacturing. So what are the materials used in additive manufacturing? Because the core topic is on materials, right? So my students' research is on materials. So I wanted to talk more on that, and that's how I thought maybe I'll give this background, how it started, where it comes from, right? And material use in additive manufacturing. So there are a lot of materials being used, right? I mean, there are variety of materials. People are trying ceramic, smart material, electronic. Now there is a 3D printing of, in our research center, they are experimenting 3D printing of PCB is and there are biomaterials, composite materials, hybrid materials, alloy. Someone was asking, right, whether we can use alloys. Yes, nowadays alloy materials are coming. Polymer materials are, I talked about, showed you a lot of polymer products. Metallic is also now very matured. Metallic polymer is very matured. Now all other probably are still, uh, kind of in a trends. We don't know where, and then they in a next few years probably they will mature and they will become one of the mainstream material, the way today polymer and metallics have become. And to some extent I would say alloy will also become, because if you are able to do the metallic, and maybe alloy metallics would probably will able to do successfully. But in future maybe biomaterials, you know pharmaceutical application related materials, or electronic side of application of materials, or food side of, maybe they are still very initial stages, and may take some time. So although as I said, most common today in a common man's life is a plastic, right? And there are also plastics of different grades. I'll talk about that. And then resin is another polymer type of material. And then now the composite. Someone was asking, I just listening to the earlier lecture, whether composite, but there are different meanings of the composite. I mean, if you are talking about the laminated composite, yes, there is a kind of different technology. If you see, probably maybe lamination, sheet lamination kind of technology. But if you are talking about the metal matrix composites, or you talk about those kind of composites, probably people are doing lot nowadays, and that's my students work about. And then the metals I already said, and maybe in future you will have more Today it is not more commercial because technology has not matured much, but in future biomaterials or food materials or pharmaceutical materials might become very common. And who knows, maybe you will get a machine to print your own pharmaceutical medicines. So in a FDM 3D printing, mostly the plastics. So maybe very standard plastics today, very common plastics are PLA and ABS. Then another engineering category plastic, lot of those are TPU, and many of those I have used nylon, PET in my startup. Probably advanced plastics I have not used much, but they are there. And lot of, but our work was around PLA and ABS. And as you move above, upwards, then performance, temperature requirements, and cost will keep changing, and it will be so these are low cost. Maybe cost increases, temperature requirement increases, performance strength wise also increases when you move from bottom triangle to the upwards. And one of the things which I want to talk about, then the PLA and ABS are, although they are very standard plastics, but PLA is a thermoplastic, and it is also has become very popular in a biomedical application because of its relative good strength and biocompatibility and biodegradability, and as well as simple processing and modification. That was one of the thing which has led our gave the direction to our research also. So there are some characteristics of this 3D printing, and so PLA has low impact strength, although it gives a good, excellent visual quality and finish. That is what why I was using, because I wanted to make a good look, good finish products, and but it has a strength, and that is where how I started playing with the. I used to do a lot of experiments with my that Z code and the way parts should be printed and all, and play with those printer parameters to get the good strength in PLA. Nonetheless, I mean, if the material itself has a low strength, we really can't do much. But the one thing that was our choice was because it is a very good in a finish and look and all that. But all common products, whatever you have seen, are were not really made for the strength, right? So maybe my headset, if it is, if you just drop it standing on the floor, probably it will break. But I'm not expecting, right? I mean, someone to drop it. So maybe if I have to make it non-breakable on dropping, maybe I should look for maybe a nylon or maybe ABS or maybe maybe a resin, right? But that will increase the cost, and I was looking to make the products which were low cost. And that Pac-Man game, we made it such a way it won't break easily. So that's the thing we were doing with our products. Now, what are the challenges with the in a plastic 3D printing? Are some of the challenges, again coming from my own experience, and I have then picked up some pictures from the internet just to make it clear. So there are challenges with respect to application. What is the application of that 3D printing? What is that type of 3D printing in a FDM plastic? What your size of object, and the features of the object? What is the printer you are using? What is the material you are using? What are the machine parameters using? So these are the parameters that my student has then listed in his thesis, where we identified the part design, I mean feature complexities, whether they are thin, thick, or lot complex, or whether the part is printed in a certain orientation or different orientation? What are the, how they affect the strength, these parameters, process parameters, material, which kind of filament, does the filament color has any impact, or filament diameter has any impact, or melting temperature and any additives into the material has any impact? What type of machine, whether it is a Cartesian type or different kind of machines, is there any impact on accuracy? How the operating parameter, humidity, cooling, operating temperature affects your 3D printing? So these are all used to lead different kind of complexities into the 3D printing. Like sometime you may not get that extrusion start, it is not sticking to the bed, or sometime it is under extrusion, you can see, sometime it is over extrusion, sometime gap in the materials, or stringing, oozing, right, or overheating. And that is, this is, these are the most of the challenges we observed in that all product whatever we manufactured. And most we have seen into that VR headset, one single piece, not the DIY kit, and then that face shield, a big helmet kind of face shield. So we have seen those many of layer shifting, and layer shifting was very common for thin parts, and it is it affects, and will talk about, we did the analysis of that later. And then there are layer separation, because when the part like this helmet part used to become, or this our VR headset was almost 180 in height, and this helmet kind of face it was also around 200. So by the time we print the top layer, probably we started seeing some of these into that. And then clogging become one major challenge in my PhD students, because of, it's again because of the nature of the material we are trying to use. But in normal PLA also it is very common, sometimes weak filling, blobs, and there are filament related issues, and those lot of those challenges we have tried addressing. And because we were coming across these all challenges, because most of my products were thin products, most of the, even the PhD student who use was a thin product. Because of the, if this would have been slightly thicker, probably we could have got a better we would not have faced many of these challenges. So this is what I mean. Wrapping was one of the common issue. I had to struggle a lot to ensure my product VR headset doesn't wrap by the time I finish it. So we had to think of the ways and means to ensure it doesn't wrap up, right? All that, or even, and because the thickness was maybe maximum thickness into that product was 2 millimeters in any wall. 2 millimeter was the maximum thickness, you can imagine. And many other products also were so thin. Even my then student has, therefore our specimens for strength testing were in that range. We created extensively work for that. So these are the some of the things we observed, and that is why and then that helped a lot. I mean, we did not really try to address these in our research, but these, my observations, my experiences while manufacturing my own products help me to guide these a couple of students to in their research. So what he wanted to do was, he wanted to do the PLA, composite PLA for biomedical application. And why PLA? As I said, PLA is a biocompatible, and PLA is now approved by FDA for medical application. And maybe it in future in the research, if you see, people are now trying to use the PLA for implants, tissue engineering, drug discovery, wound management, and variety of purposes. And that is why we wanted to make sure how can we make a better PLA, can we make a better different PLA considering the biomedical application. And then we started looking at one of the proposal he made was composite PLA. Then we started looking at what way we can do the composite PLA, how the researchers are doing it, right? So people probably fiber reinforcement composites. Maybe we also thought of, can we now use some metallic filaments within the filament, or can we? But then question was whether it should go through the spool and then melt, or then how are you going to ensure the melt, or maybe can we put some finite length microfilaments while printing itself. I mean, a lot of that research we are trying to find out, how do we get or can we do a nano composite, or can we do, then we came across a lot of researchers are also doing something called a particulate composite, adding different kind of particles into the PLA material, that is a polymer, different polymers to improve the PLA performance, ceramics or metals, other materials, and all that. So we were experimenting, we tried almost all, but finally we realized, oh, within our laboratory environment or within our own constraints, we may not able to do any of this. Maybe we will go ahead with this, and that's how we decided to use the. So then we did a more elaborate research, and we saw, oh, a lot of researchers are already using metal particles into the PLA, like copper, steel, bronze, titanium, magnesium, iron, nickel, all that. And also we came across there are already some commercial PLAs which comes with the metallic particles into it. So it, I mean, then, but when we did this study, we realized none of this is suitable for except this titanium probably is not suitable for a biomedical application, and commercially available definitely not suitable. So, and we wanted to make the PLA for biomedical application. And then what novelty we can have in our research, and we decided to use, and mainly primarily he wanted to use, I don't remember the, because he approached me probably after submitting his proposal to the PhD and getting the admission. And then I remember he mentioned specifically cobalt and chromium. I don't know why it was. And then we wanted to make the cobalt and chromium into the this one. So, but through the research, it is observed that no one has used cobalt and chromium, either single particle or mix. And we wanted to create a 1.75, which is a common commercially available filament, by adding cobalt and chromium particles, which are more suitable for medical because they are bioinert materials. And we wanted to investigate, can we use this PLA on this Ender 3 low cost printer, so that it can be, common available in the medical facilities, small printers. Because if I create a new material, I should not end up requiring a new 3D printer, right? I mean, then it will become a circular thing. Oh, I create something, I need something special. So we wanted to stick to the low cost commonly available 3D printer, the same size of a diameter, and then try to use it. So, and then maybe because, as I said, I mean, during my those product design days for 3D printing, I came across a lot of parameters of it. So I asked him to study what is that, and specifically focusing the orientation, because I observed through my own research, I mean, practical uh, experience into my product, that orientation has a major impact than any other thing. And so I said, maybe let's have this let's study all the parameters and see is still if the orientation is the major factor to study for any of the product. And one of this one reason, another reason was, see, any complex part can't have just one orientation. It will come with a combination of orientations for different regions of the product. So that is what we observed. Now, for example, we selected one application was this, let's say finger splint, okay, external. We really don't want to do the internal part. Again, we never had this biomedical testing and all that capability. So we thought we'll go ahead with some medical device which is externally used. So the whole approach was 3D, more around the tensile test specimen using commercial PLA first, manufacturing our own PLA, manufacturing PLA by adding this cobalt chromium particles, do the tensile test experiments, and then do the analysis of loads, effect of orientation. Orientation, I'll talk why we wanted to study the orientation. I said it was the most common based on my own experience, but we also wanted to address the product design related challenges, and then comparison with variety of other analysis of fracture, analysis of microstructure, and all that. And then what we did to begin is we bought commercial PLA. So this is what was the reason. So if you see this finger splint, if I am printing in this way, see different regions have the different orientations. Maybe this, if I take a tensile test specimen here, some regions are vertical, some regions are inclined, some regions are maybe inclined on the edge, right? Some are on the flat on the bed, right? So these are the all considering the possibilities for any complex product. We'll have variety of orientations. We started, I mean, different names are used in the literature. They may simply use X, Y, Z or upright, flat, edge and all, but we came up with a common terminology. The flat is means on the bed, flat with support means, oh, I'm not directly printing, like for example this top one, I'm not directly printing on the bed, but there will be support. So flat, it is a flat part, but more like this region, but on a support, right? And then this is a maybe more this particular, it's not on the edge, but edge on the support, right? And then there is a this region, if you see, this is on edge 45, right? Then this region probably here is upright 45, this region. And there can be if there are some vertical regions, it will be upright. So all that considering, we tried considering 5 6 orientations which can be there. There can be intermediate, but we just chose a one angle, that's the middle angle, rather than choosing multiple angles. It was too much. And then what we did, the first thing first we did in the research is, oh, let's print these orientation specimens. And then we wanted to do both bending and tensile, but over the period of time we realized bending is too much, lot of, because it is a more lot of effort, so we just stick to the, and then we did a study. Oh, what is the strength? I mean, this, a lot of that I knew qualitatively, through my experience in my products, but we now created a scientific understanding through the research that, okay, and then these 6 orientations clearly fell into the 2 categories. One is a strong orientation group, that's flat. So this is the one. And then edge, this is an edge when you print on the edge. And then flat support, they become a strong. These parts definitely were always strong, and that's what my experience was expecting. And these upright 45 and edge 45 become a weak in both the cases, whether it is a bending strength or whether it is a tensile load. So in both the cases, we came across there are clear and the orientations are the same. It's not, maybe uh, the strength might have slightly changed. Maybe like here the weakest is a upright 45, where here it is the weakest is upright. So that sequence might have changed within the group, but the two groups formed were clearly the same. So we tried doing mathematical modeling and thought, can we use it and all. And again, as I said, all these parts were having three thicknesses. One is 1.2, 2 mm and 2.8, because this is again based on the kind of part thickness this has, but again it mainly derived or driven by my own product. My products were not less than 1 or not more than 3, so we stick to some range. And more because this research is more primarily useful for the thin parts. If you are looking for thick parts, probably the insights from this research may not be useful. And then we also created the analysis of fracture, uh, both in bending and tensile. So if you see, what we observed is, in case of the flat part which was printed on the bed, then we saw it's a more traditional fracture, right? Zigzag kind of fracture, which was because the part was stronger groups failed with the zigzag crack, whereas they were weak in a group because the layer they failed along the layer direction. That's why they become a, because layers were weak, and these weak layers created a uh, easy sites for a fracture. So you can see here some of the tensile also has the same thing. So these are the actual pictures from the bending. These are the actual pictures from the tensile. You can see the kind of, for the flat support, more like a zigzag, even for the edge. But for the edge 45, upright 45 and upright, it's along the layer. So that's analysis of fracture for the commercial filament. Now the next part of the research was focusing on manufacturing our own filament. Before even we add a material particle, we thought we'll add our own will create. And then this was a big challenge, getting that this Prabhas Katiyar was a student, and this became one of the key major effort in the research, identifying how to manufacture it, which equipment to use it. And we were not able to, we contacted a lot of commercial manufacturers, many of them probably not agreed to manufacture that particle based filament. So we had to think about our own, creating our own environment, and we created using this PLA granules we bought. We found some research center where, I think in the Uttar Pradesh, he found some, I don't remember now. And then we found machines which could create this 1.75 filament segments. We could not even manufacture the long filaments, but that's still okay for the research. We wanted to prove that. And then after creating this PLA filament without adding material, we wanted to check how our own PLA stands comparison with the commercial standard PLA. And we this was the machine within which we had this kind of dyes of 1.75, and these were the specifications of the granules. And then we followed a certain process of extrusion, melting and extrusion to get that finished filament. And once we got that, maybe we didn't compare it. You can see now, I mean, it stands very clearly. Maybe commercial PLA, these dotted lines were showing some higher load capability than the in-house, maybe because ours was a segments, and maybe we could not, we are not sure of what PLA granules they use, what PLA raw material they use. We assume we tried matching that property with the granules, but maybe that is one of the reason it has that variation. And it also showed the similar trends, right? All strong and weak group. And additionally, we did some analysis, some more analysis why they are not matching, and this probably could have been done for earlier part also. We observed there is something called stare effect, and that stare effect became one of the uh, understanding for future how the fracture behaves, right? So the thickness maybe 1.2 or 2 or 2.8, right? And when you are printing in a different orientations there, if you are flat or edge or upright, probably you don't see the stare effect. But whenever there is a inclined, orientation, this became a, and that was one of the reason where um, this has also played a critical role, the way it fractures. If there is a stare effect, then it is a fine kind of fracture, easy fracture. If there is a no stare effect, then it was a more strong component and failed with the, and that is what we checked, what is happening with the fracture, layer strain, layer area, and lot of those analysis. We, how much is a joint area, what is the area of resistance, and how that is correlated. So when we tried doing analysis, probably we tried validating with the mechanics behavior of the failure. And then final thing, we created a cobalt chromium PLA filament, because cobalt chromium, we know, I mean, we started facing a lot of issues with our in-house PLA filament with the some nozzle related challenges we observed. So we did not want to add a huge percentage in the beginning. We started with low, we started with 0.5% cobalt 0.5 and chromium 0.5, so it is a 1% together in the PLA. The powder form, it was a powder form, again those granules. Now the same process we followed, melting and extrusion, and we then, because of this cobalt chromium adding the same PLA granules, you can see the change in the color. Instead of white, they become now darker with the more percentage, they become the darker. So then we manufacture those different, and then again we compared the strength, load capacity of, and then we found this is a commercial PLA, which is still highest uh, uh, loads. Then you have in-house PLA, and then we found as we add material, particles, metallic particles, load started decreasing, and probably that is most of the cases load decrease with various range. Some places we saw some bit increase, but probably it's not that significant. And that also analysis of fracture also lead, maybe now different type of fractures we started observing, not exactly similar, maybe because these particles played a role into fracture. And then we created 5 different splints. We tested it, and strength, usability, look and feel, and all that. So we did a lot of that, and successfully my student completed the research. One of the challenge we observed was this. Nozzle clogging started a major challenge because of the metallic particle, and 1.5% faced lot of that. And That is why we did not want to add more than 1.5, which is a 3%. And then we also needed a more temperature settings and so on, because temperature, same temperature was not definitely, and we wanted to keep as much as the same printer parameters, but some of these we had to change. Maybe we had to change temperature, we had to change the speed, and those things we had to do. So then that was the one. Maybe I'm almost coming to the end. And another student, I don't want to talk a lot about that, but same, another student in Pune worked on a building a artificial intelligence model for knowing which orientation, what kind of orientation I should be using for that basis that experience. And she has also completed her thesis. Both have completed thesis and defended thesis. So but I'll talk about this in some another forum. I wanted to talk more about something. I don't know, we don't have time, but we had a very state of the art 3D printing machines in our research center. Maybe I will show you one. Maybe this is one of the world's largest 3D printing. Probably, I mean, in this category, probably this. I'll just play the video. Maybe with that we can make a full stop.
What makes a meld process unique is that it's solid state. There is no melting. We stay below the melting temperature. And this is what results in a number of really great characteristics in the build. Not only do we see really great material properties, but our deposits are also fully dense, meaning that the part doesn't require a secondary step. And there's very little waste. It's a very green process.
We're very passionate about the meld process, and we're very driven to see it take off, proliferate throughout industries. So the machine itself is a very robust machine. It's capable of processing your soft materials like aluminums up to your nickel alloys. It's repeatable. It behaves like we want it to behave. The automation system we put in place performs as you expect it to perform. And it's able to do what you tell it to do. So you can able to program in your geometries you want and come back to the same thing every time you want to do it. When you compare the melt process to conventional additive manufacturing processes, we're putting down a lot more material, a lot faster. So if you're looking to build very large components quickly without additional processing required, this is a good opportunity for that. So when the customers reach out to us, we're equally as excited to educate them and inform them about the process and technology, and excited to work with them and figure out how this process can help their needs.
We can repair unweldable materials, join or coat dissimilar materials. So the options that this process creates really opens up new product opportunities. Everyone involved in the manufacture of metal or metallic components has or should have an interest in this process.
So this Europe's largest machine is at on our research center. So I will not speak about other machines, but that's one of the, you have the metallic rods. You melt, I mean, not actually melt it, but while you are depositing, more like a friction stir welding, you reach that more melting and then deposit, and melting and deposit the way you want, and then do the finishing, and that is how you get the complex part. And that is one of the core research our research center does. So to conclude, 3D printing is an additive manufacturing process to print any object. Today, it is very commonly used across the product life cycles. There's no more prototyping, but it is a more of a product manufacturing becoming now today. And the FDM is most popular in the common public. Industrial, there are a whole set of different printing processes and technologies. Several materials can be used, from metals to plastics. I talked more about the plastics. we went through some of the challenges and then how to overcome some of the challenges for the biomedical application and all that. I hope that was useful. Thank you very much. And if there are any questions, uh, I'm happy to take. Dr. Kiran, probably I took a couple of minutes more, but I think.
Yes, sure. Hmm. Sure. So over to participants. We'll give a chance to participants to interact if
Mhm,
they have questions.
mhm.
Yes, participants, if you have any question, please feel free to uh, drop a
Sir,
question.
I've posted a message on chat. I've posted because I'm traveling. I
Okay.
Yeah, Omkar, I'll see that. Yeah,
Yeah.
see that.
I think, yeah, he has mentioned, spoke about the future of 3D printing, how far we are from printing our aircrafts, and what could be possible layup method used for. As I said, I mean, some of the industrial printers are actually printing lot of aircraft parts. So maybe complete aircraft printing, we are very far away, but yes, uh, additive manufacturing is being extensively used in various parts, including composites, including titanium parts, including, and as I said, our research center particularly is very closely working with companies like Airbus, Boeing, which is doing lot of research for the aerospace industry. I hope that helps clarify.
Yeah, any other questions?
At least not
Good
there in
evening,
the
sir.
chart, but yeah, yeah, yeah.
Yeah, Deepak.
Good evening, sir. Deepak Kharat.
Yeah.
Sir, know to me. Sir, I want to ask what are the type of project or to give to the final year students so they are adapt with this type of technology and all the stuff.
You can give any, you can tell them to print any mechanical products, right? You can tell, oh, pick up any product from your uh, vehicle or bicycle, or make the 3D model and print it, right? They can probably do it. Or ask them to think what can be, what you can replace in your day-to-day life a part which you instead of buying, maybe make it, right?
Thank
Okay,
you, sir.
thank you. Any questions? Yeah, there is a question in chat box from Professor Kunal.
Yeah.
Sir, any time and cost analysis and comparison of 3D printing with injection molding for mass production?
Yes, that's a very good question, and that is what one of the thing I was just dwelling when I was doing this my VR headset printing. One point came. I was thinking whether I should now go for injection molding, or I still continue printing with the 3D printing. And that, when I did the cost analysis, how much I sell, how much time it takes, and what is the demand. It all depends on the demand. If there is a very huge demand and you want to do the same product again and again, from cost point of view, injection molding is still better. But if demand is less, or if you want to make a customized product, let's say my VR headset, one of the things we were working is, we'll make it unique for your order, make it to the order, right? So there probably injection molding might not work because I can't tailor it easily. That is how I, I was trying to do the cost analysis. If my product is, or my offering is tailored, then injection molding won't help. But if my offering is a common product, same, and there is a huge demand, and because 3D printing has two things, time and cost. Time, it takes more. I can't, one point came in during COVID rather. where I had to buy another printer. I mean, I was having already two printers. I had to buy another printer because I was not able to meet my Amazon orders. So that time I decided whether I should now buy one more printer or I should go for injection molding, and I still felt maybe I have not reached that break even. So that kind of break even analysis you will have to do for. I hope that answers your question.
Yes. Thank you from the Professor Kunal Bowser, as he mentioned
Yeah,
in the
yeah.
chat.
Thank you, thank you.
Yeah. Any other questions from the participants? Participant, please feel free to ask the question.
Yes.
Any other questions? I think no more questions, Dr. Datta. So
Thank
thank you.
you.
I
No
request
problem.
Disha to provide vote of thanks. Disha, over to you. Disha, you are mute. You are on mute. Yeah.
Good evening, everyone. I sincerely thank our speaker for giving us useful and productive session. It will definitely help us in our future projects. I also thank for all the faculty members and organizers for their support. Thank you everyone for being here today. Have a great night.
Yeah. Thank you,
Thank
Dr.
you,
Kiran.
Dr. Datta.
Uh,
Yeah, thank you.
yeah,
Thank you very much. Thank you for
Yeah, thank you,
spending
sir.
time.
thank you.
I think it's very much cold there in UK.
Yeah, right. Nowadays it is almost reaching zero. Okay. See you when I come in India. I'll let you know.
Yes, yes, sure,
Thank you
we'll
for
meet.
invitation.
Yeah.
Bye bye.
Thank
Bye
you. Thank you.
bye.
Bye. Take care.